Everything we call real is made of things that cannot be regarded as real. These profound words uttered by Niels Bohr, one of the foundational architects of quantum mechanics and a Nobel laureate, serve as a potent incantation, inviting us to delve into the very bedrock of our perception. They whisper of a reality far more intricate and elusive than our everyday senses might suggest, prompting us to question the solidity and inherent truth of what we take for granted. Imagine, if you will, a moment, unbidden and inexplicable, arising amidst the most mundane of days, when something fundamental within your psychological landscape irrevocably shifts. The world around you, once so tangible and undeniably present, begins to recede, losing its inherent authenticity. It's as if a thin, translucent veil, previously unnoticed, suddenly descends, muting the vibrant hues, dulling the sharp contours, and softening the crisp sounds of your environment. What was once a rich, three-dimensional tapestry woven with undeniable threads of experience now flattens, transforming into a mere backdrop, a stage set, a meticulously crafted facade that lacks the visceral presence of genuine reality. Your own hands, your feet, the very limbs that have served you faithfully throughout your life, continue to respond to your will, yet their sensation is utterly altered. They no longer feel like intrinsic extensions of your being, but rather as highly sophisticated prostheses, perhaps marvels of engineering, yet utterly divorced from the deep, embodied sense of self. The motor commands are executed flawlessly, but the proprioceptive feedback, the comforting sense of inherent ownership and connection, is muted, replaced by a chilling sense of otherness. It's an uncanny valley sensation, where the familiar is rendered strangely alien, as if your consciousness has retreated to an observational outpost, watching its own physical form operate from a detached, almost clinical perspective. Further still, you find yourself caught by a disquieting thought, a notion that should be dismissed as absurd but which stubbornly entrenches itself. The faces of even your most cherished loved ones, those with whom you share the deepest bonds of intimacy and shared history, begin to radiate an unsettling, almost extraterrestrial falseness. It's not a visual distortion in the conventional sense. Their features remain perfectly recognizable. Rather, it's the emotional resonance, the vital spark of connection that defines human interaction, that seems to vanish. They appear as exquisitely sculpted masks, impeccably detailed yet utterly devoid of genuine inner life, their expressions flat, their voices sounding like recordings played back from an immense distance. The very essence of your shared humanity seems severed, leaving you adrift in a sea of emotional void. And then there's time and space. These fundamental, unyielding dimensions of our existence, they begin to behave in a manner that can only be described as profoundly bizarre, a veritable madness. They stretch and contract with a terrifying elasticity, defying their usual linear progression. Moments might distend into eternities, each second unfolding with an excruciating slowness, every action seeming to unspool in a dreamlike, protracted sequence. Conversely, hours might vanish in an instant, entire segments of your day dissolving into an amorphous blur, leaving you with a disorienting sense of lost time. Space, too, becomes malleable. Distances feel immense even across a small room, or conversely, claustrophobically compressed, as if the very fabric of geometry is twisting around you. The fundamental scaffolding of existence, the very framework that defines our reality, becomes warped, unreliable, and deeply unsettling. The entirety of reality itself assumes a distorted, distant, and profoundly surreal quality, as though you have been thrust, without warning, into a vivid and inescapable dream, a lucid nightmare from which the escape button seems irrevocably broken. You are disoriented, unmoored, grappling with a profound and disquieting sense of foreignness as the anchor to consensus reality loosens its grip, allowing you to drift in an ocean of subjective strangeness. If such a scenario strikes you as purely the product of artistic license, a dramatic embellishment from the pages of science fiction or the silver screen, a fantastical impossibility, then I must gently disabuse you of that notion. Fleeting, episodic manifestations of this very state, clinically termed derealization, are not uncommon. Indeed, they are experienced by a significant portion, perhaps even the majority, of individuals at least a few times throughout their lives. These temporary excursions into the unsettling realm of altered perception are far more prevalent than one might intuitively assume. Thus, if you have to this point remained untouched by such disquieting symptoms, it offers no absolute guarantee that they will never manifest. Life, in its intricate and unpredictable unfolding, often reserves surprises for us, and the boundaries of our own consciousness can, at times, become surprisingly permeable. Perhaps one day, amidst the tranquil passage of an ordinary night, you will awaken, or believe you have awakened, and be gripped by that profound uncertainty. Are you truly conscious and in the waking world? Or are you still ensnared within the intricate, often indistinguishable web of a dream? This specific brand of cognitive dissonance, this liminal state between the known and the unknown, frequently arises during the delicate transition from slumber to wakefulness, leaving in its wake a lingering trace of mild anxiety and a deep, introspective pensiveness about the nature of our perceptions. In the iconic 1999 cinematic masterpiece, The Matrix, the protagonist Neo finds himself grappling with precisely these inexplicable and deeply unsettling sensations. He is consumed by a pervasive, visceral conviction that the reality enveloping him is fundamentally inauthentic, that something within its very fabric is profoundly amiss. This particular psychological state bears a remarkably apt and descriptive designation: derealization. Despite its observed prevalence, the precise neurobiological and psychological mechanisms underlying the onset and experience of derealization remain, to a significant extent, poorly understood by contemporary science. It is a frontier of psychological inquiry that continues to challenge researchers. However, the sheer statistics are arresting. For instance, in Canada, the very nation that is home to the actor who so memorably portrayed Neo, nearly 1 million individuals report encountering symptoms of derealization within the span of a single month. This staggering figure underscores not only its commonality, but also the quiet, often unarticulated, struggle many face. Should you ever find yourself experiencing the bewildering symptoms of derealization, you will swiftly come to appreciate the profound difficulty inherent in attempting to articulate them. It is as if the lexicon of human language, usually so rich and nuanced, suddenly proves woefully inadequate, lacking the precise shades and fitting metaphors required to convey such a subtle yet utterly pervasive transformation of perception. It is akin to endeavoring to describe the vibrant spectrum of color to an individual who has been blind from birth, or to explain the intricate complexities of a symphony to someone who has never heard sound. The very tools of communication fall short. I find myself compelled to explain why you are here, at this very moment, absorbing these words, these whispers of possibility. It is because, deep down, you have sensed something, an intuitive recognition, an almost precognitive understanding. You may struggle to articulate it, to give it form and definition through language, but you feel it, a quiet hum of unease, or a spark of profound curiosity resonating within your core. The English Wikipedia, in its attempt to categorize and define this elusive condition, offers a description that, while clinical, captures its essence with remarkable clarity. It may seem that the individual is looking at their immediate surroundings through VR goggles, through a pane of glass, or at a cinema screen. Individuals may report that what they perceive lacks vividness and emotional coloring. The emotional response to the visual recognition of loved ones may be significantly reduced. The individual may not even be certain that what they are perceiving is actually reality. This portrayal perfectly encapsulates the sensation of estrangement, as if an invisible, impalpable barrier descends, separating you from the world, rendering it flat, distant, and emotionally devoid. It's a profound sense of detachment, a feeling of being present yet simultaneously absent, observing your own life unfold as if it were a meticulously produced film. This persistent internal murmur, "You have always felt that something is wrong with the world," is not merely a peculiar thought, it is an intrinsic call, a subtle yet persistent questioning that permeates the very fabric of your existence, nudging you towards deeper contemplation. A critical distinction, often overlooked, lies between the experience of hallucination and that of derealization. During a hallucination, an individual perceives or senses something that is, in an objective sense, not truly present in the external world. They might hear voices that aren't there, see objects that don't exist, or feel sensations on their skin without any physical stimulus. In contrast, with derealization, the individual neither hears, nor sees, nor feels anything that is objectively unreal. Instead, their perception of actual external events is altered. Everything appears distant, shrouded in a pervasive mist, or eerily dreamlike. It is a distortion of perception, not a creation of it. Frequently, this state is accompanied by the peculiar phenomena of déjà vu, or jamais vu. The sensation of déjà vu, or already seen, is perhaps universally recognized. It is that sudden, inexplicable conviction that you have experienced this precise situation before, that this very moment has already unfolded, or that you have somehow witnessed it all in a dream. Every gesture, every spoken word, every minute detail seems uncannily familiar, yet simultaneously, a logical part of your mind acknowledges the impossibility of it, knowing that this is, in fact, the first occurrence. It creates a fascinating cognitive dissonance, a momentary, bewildering clash between memory and present experience, leaving a subtle trace of disquiet. Conversely, jamais vu, meaning never seen, stands as the complete antithesis to déjà vu. It is an abrupt and unsettling feeling that a familiar place, a person you know intimately, or even a commonly used word, suddenly appears utterly unknown, foreign, or bizarre, as if encountered for the very first time. Imagine gazing upon your own reflection in a mirror, and for a fleeting instant, it morphs into the visage of a complete stranger, alien, and unrecognizable. Or consider uttering a word that you have spoken countless times, only for it to momentarily lose all meaning, transforming into a senseless jumble of sounds. This sense of profound unfamiliarity can be profoundly disturbing, a momentary rupture in the continuity of your personal world. For some individuals, this disorienting experience can even trigger a full-blown panic attack, a sudden surge of overwhelming fear and anxiety, as the very foundations of their known reality seem to dissolve. Therefore, should you ever find yourself experiencing the bewildering and unsettling symptoms of derealization, it is paramount to resist the urge to amplify your anxieties, to avoid spiraling into self-created fear. Remember, these experiences are often temporary. With time and a conscious effort to remain calm, the world typically restores itself to its familiar order, as chronic derealization, such as that depicted in The Matrix with Neo, is a relatively rare and more persistent condition. And after all, in the narrative of The Matrix, the protagonist's profound sense of unreality is not born from an internal psychological disorder, but rather from external, verifiable circumstances. His world is, indeed, fundamentally unreal. It is a sophisticated simulation, a grand illusion meticulously crafted by sentient machines, to which all of humanity has been unknowingly tethered. I must confess a certain indifference towards The Matrix as a film, despite its monumental cultural impact. My initial encounters with the simulation hypothesis, too, left me rather cold, perceiving it as a somewhat simplistic, perhaps even flat, metaphor for the profound complexities of existence. It felt, at times, like an oversimplified answer to the deepest philosophical questions. Yet, The Matrix undeniably transcends its cinematic origins. It is a cultural phenomenon of unparalleled scale, an artifact that has etched itself deeply into the collective consciousness of humanity. You would likely need to traverse hundreds of kilometers, cross vast geographical and cultural divides, to encounter even a single individual who remains entirely unaware of this film's existence. On IMDb, the world's largest and most comprehensive database for cinematic information, a digital nexus visited by 500 million people monthly, The Matrix commands an impressive 16th position in its global rating. To contextualize this, it stands at number 16 out of a catalog comprising over 700,000 films. This extraordinary achievement cannot be attributed solely to its groundbreaking action sequences, its genre-defining, innovative special effects that revolutionized visual storytelling, or its intricately choreographed fight scenes, though these elements were certainly significant. The true testament to its enduring power lies elsewhere. If you venture into the sprawling landscape of YouTube channels dedicated to the intricate analysis of cinematic meaning and deeper philosophical undercurrents within films, you will, with an overwhelmingly high degree of probability, discover that discussions and reviews specifically related to The Matrix consistently rank among the most viewed and engaged with content. This is remarkable, especially considering it is occurring a quarter of a century after the film's initial release, a testament to its timeless relevance. Prior to The Matrix, the concept of a simulation hypothesis resided largely within niche academic circles and obscure philosophical texts. The absolute majority of people remained entirely oblivious to such an idea. But then, in 1999, the film exploded onto cinema screens, generating an effect akin to a cultural atomic bomb. It was as if this profound, unsettling theme had always lingered, unarticulated, in the collective subconscious, a question hovering in the ether, simply waiting for someone to finally give it voice, to clothe it in a compelling and accessible narrative. The film tapped so directly and profoundly into the very nerve of humanity, striking such a resonant chord with universal anxieties about reality and control, that by today, for myself, for you, and for countless others who might have already clicked away from this video, the sheer ubiquity of the topic has become almost tiresome. And it is precisely because this idea has permeated our consciousness so thoroughly, to the point of inducing a certain fatigue, that, ironically, there is a very strong possibility that there is indeed something profoundly resonant and true within it. The precise origins and mechanisms of derealization, as previously acknowledged, remain elusive, shrouded in the still developing understanding of the human mind. However, what if, and this is the crux of our inquiry, what if, mirroring Neo's experience, this state, which statistical data suggests is familiar to a majority of our planet's inhabitants, is not merely a perceptual disorder, a transient glitch in our internal processing? What if it possesses roots that delve considerably deeper, pointing towards causes that are more fundamental, more systemic, than a simple neurological anomaly? What if it is not an error within our perception, but rather a profound insight about reality itself? To unravel this intricate tapestry of possibility, I embarked upon an intensive, 2-month journey of information gathering, immersing myself in a vast ocean of academic papers, rigorous scientific debates, and ancient as well as contemporary philosophical treatises. My primary curiosity was directed towards the insights offered by the world of physics, for who else could one reasonably consult when contemplating the most fundamental underpinnings of reality, the very nature of the universe we inhabit? Within the confines of this discourse, I endeavor to distill and present, in a concise and palatable form, the entirety of what I uncovered, offering the most intriguing, and at times unsettling, conclusions. Should the thought arise that this entire exercise is nothing more than an elaborate expenditure of words, a futile philosophical endeavor predicated on the premise that even if we were, in fact, residing within a simulation, we would forever lack the capacity to conclusively prove it, a notion often presented as an unassailable truth, then I must hasten to offer a gentle, yet firm reassurance. That particular assertion is not entirely accurate. Furthermore, and perhaps more surprisingly, humanity already possesses historical precedent in substantiating claims of a similar, albeit less grandiose, nature. Consider the film The 13th Floor, released in 1999, mere months before The Matrix, a cinematic exploration inspired by Daniel F. Galoui's visionary 1964 novel, Simulacron 3. This novel stands as one of the earliest literary depictions of virtual reality, a prescient narrative that anticipated many of the conceptual cornerstones later foundational to cyberpunk and modern science fiction. While The 13th Floor was critically well received and offered its own compelling narrative, its success was largely overshadowed by the explosive, unprecedented global phenomenon of The Matrix, leaving many unaware of its existence even today, relegated to the shadow of its more celebrated counterpart. The most enduring and haunting sequence in The 13th Floor unfolds when the protagonist is extended an extraordinary invitation to partake in an experiment, to journey to a destination he would never have conceived of visiting, to transcend the perceived boundaries of his known world. This audacious venture leads the character, quite literally, to the very edge of his simulated reality. Beyond this precipice, the world is no longer rendered with intricate detail and convincing realism. Instead, it degenerates into a primitive, skeletal wireframe model, a stark revelation of the underlying digital architecture. This encounter with the raw, unfinished code of his existence instills a profound terror in the character, as the horrifying truth of his simulated reality dawns upon him. While such a scenario played out on the cinematic screen undeniably possesses immense visual spectacle, dramatic tension, and visceral impact, one must ponder how many of us, upon sober reflection, would genuinely desire to inhabit the shoes of that protagonist, to be confronted with such an unsettling and reality-shattering discovery. The thought itself evokes a deep existential disquiet. In a recent article published in The New Yorker, focusing on Sam Altman, the current CEO of the company that pioneered ChatGPT, a fascinating observation was made. Many individuals in Silicon Valley have become consumed by the simulation hypothesis, the assertion that our perceived reality is, in fact, a construct generated by a computer. Two technological billionaires have taken this belief so far as to secretly engage scientists to embark on a mission, to devise a method for extracting us from this very simulation. This immediately raises a multitude of profound questions. What precisely does this work entail? In what specific forms is this research being conducted? My immediate inference, and a logical one at that, is that before any attempt at extraction can be made, these scientists must first establish, with irrefutable certainty, that we are indeed dwelling within a simulation. The primary hurdle, therefore, lies in substantiating the hypothesis itself. So how might they achieve this? What methodologies, what forms of empirical evidence could possibly be brought to bear on such an extraordinary and far-reaching claim? Let us engage in a thought experiment, one that might illuminate the path to such a discovery. Imagine yourself as a character within a sophisticated video game, one that, to a reasonable approximation, meticulously mimics the physical laws and sensory experiences of our own universe. For the sake of illustration, let us select a widely recognized and expansive title, such as Grand Theft Auto: San Andreas. Were you, a conscious entity within the confines of this game, to harbor a burgeoning suspicion of your simulated nature, how might you go about confirming such a radical hypothesis? Indeed, the most immediate and intuitive approach, much like the revelatory scene in the 13th floor, would be to systematically attempt to locate the inherent boundaries of this simulated environment. Given that the land masses within the game are unequivocally encircled by an apparently boundless expanse of water, a logical initial step would be to acquire the fastest available watercraft and embark upon an audacious journey, seeking out the very edge of this digital world, the point where the illusion might fray and the underlying code could become visible. Within the meticulously crafted digital realm of San Andreas, the expansive game map spans an approximate area of 6 by 6 kilometers. It is evident, from a computational design perspective, that the simulation was never intended to sustain rendering capabilities for a player venturing extensively beyond the predefined limits of this map. To do so would impose an exorbitant and unnecessary strain on the underlying processing resources, as such distant and rarely accessed regions are typically optimized for minimal detail. However, the architects of this digital world, it turns out, have implemented a design that is far more sophisticated and cunning than it appears at first glance, a subtle mechanism to maintain the illusion, for, despite your valiant efforts, no discernible boundary, no overt edge of the world will ever be encountered. Even when piloting the most advanced and rapid boat the game offers, your character will simply continue to traverse the seemingly endless expanse of water, moving progressively farther and farther from the discernible coastline, lost in a perpetually generated, yet ultimately featureless, ocean. The ingenious subtlety of this design lies in a cleverly implemented failsafe. After a predetermined, yet realistically plausible duration of continuous travel, your character will inevitably succumb to the game mechanic of hunger and perish, their journey prematurely terminated by a natural in-game cause, thus preventing them from ever reaching a point where the simulation might openly expose its limitations or glitches. Yet, what if, through some extraordinary means, perhaps by exploiting a hitherto undiscovered programming flaw, or through a deliberate manipulation of the game's internal code, you manage to circumvent this inherent problem, overcoming the constraints of the simulated physiology? What if you were to continue your relentless voyage away from the virtual shore, without interruption, for an astonishing period of 3 real-world months? After traversing a truly astronomical distance, equivalent to approximately 50,000 distinct in-game maps, or roughly 300,000 kilometers, a distance comparable to the span separating Earth from its moon, you would, at this extreme point, subject the game's underlying engine to unprecedented and highly atypical conditions. Under such immense and unforeseen strain, the engine would begin to manifest profound instabilities, descending into a state of chaotic malfunction so severe that your character would literally begin to visually distort, to split into multiple copies, to smear across the digital landscape, generating a cascade of visual artifacts and glitches that are unequivocally outside the normal parameters of the game's operation. While it remains unclear precisely how such an experience would be perceived from a first-person perspective within the game, were you, as a conscious character within this simulated world, to observe such an outright digital breakdown from an external vantage point, perhaps through the lens of a virtual pair of binoculars, how then would you interpret this digital madness? It stands to reason that this bizarre visual corruption, this outright failure of the simulation's rendering capabilities, would not, in itself, constitute irrefutable, unequivocal proof of your existence within a faulty simulation. However, such an anomalous situation would undoubtedly serve as the first, highly significant coin dropped into the collection box of evidence, strongly suggesting that something is profoundly and fundamentally not right with the world in which you find yourself. So we are left to ponder, with a growing sense of unease, just how right is our own, seemingly authentic world. In our ostensibly real world, the cosmic equivalent to the seemingly infinite ocean of Grand Theft Auto is the boundless expanse of space itself. And if, hypothetically, any intrepid explorer were to devise a means of traveling indefinitely through this cosmic void aboard a spacecraft, continuously accelerating away from Earth for an arbitrarily prolonged duration, then, mirroring the digital anomalies of GTA, after an incredibly extended period, an exceptionally suspicious anomaly would eventually manifest. This anomaly, once unveiled, would inevitably ignite the most profound and unsettling questions concerning the very nature of our reality, compelling us to reevaluate everything we thought we understood about the universe we inhabit. To truly grasp the essence of this looming anomaly, one must journey into the intellectual landscape laid out in a pivotal work titled The Black Hole War, penned by one of the most brilliant minds in contemporary physics, Leonard Susskind, a preeminent figure in the development of string theory. Our exploration must commence somewhat broadly with foundational concepts, but I assure you, dear listener, that the initial breadth of this discussion is not where your primary concern should lie. Rather, it is in the subsequent implications that the true weight of the matter rests. So, let us visualize a dramatic scenario. An astronaut, venturing too close to the gravitational maw, begins an inexorable fall into an enormous black hole. What, in your estimation, would be their immediate experience upon crossing the event horizon, that enigmatic boundary? Allow me to reiterate. The event horizon of a black hole is a theoretical, yet incredibly real, point of no return. Once traversed, escape becomes an absolute impossibility, irrespective of the magnitude of your acceleration. Even if you could achieve infinite velocity, you would remain trapped. Therefore, what sensations, if any, would the astronaut register as they approach and ultimately breach this critical threshold? The towering edifice of general relativity articulated by Albert Einstein states with unequivocal clarity that, at the precise moment the astronaut crosses the event horizon of an immense black hole, absolutely nothing extraordinary, nothing physically discernible, would occur from their subjective vantage point. The astronaut would remain entirely unaware that they had just transgressed the point of no return, the cosmic Rubicon beyond which all paths lead inwards. This inherent imperceptibility, incidentally, constitutes a monumental peril in the scientific study of black holes. Compounding this danger is the fact that the surface area of the event horizon is not merely an impalpable boundary, but an inherently unstable and dynamic entity, perpetually expanding as the black hole continuously accrebs and devours surrounding matter, gas, dust, stars, and even entire galaxies. Consequently, maintaining a stable low-orbit trajectory around a black hole is an exceedingly hazardous undertaking, as one might, with startling suddenness, discover that their once safe orbital path has shifted, and they are now caught within the event horizon, unable to escape. So let us return to our intrepid astronaut. Yes, they are indeed plummeting into a colossal cosmic abyss, yet, paradoxically, their immediate sensation is nothing more profound than ordinary weightlessness, precisely the same sensation they would experience adrift in any other region of open space, far from the gravitational pull of massive bodies. The true agony for the astronaut would only commence much later, hours, days, or even weeks hence, depending directly upon the immense size of the black hole. Closer to the black hole's singularity, where gravitational forces escalate to unimaginable tidal magnitudes, the astronaut would be subjected to a process known as spaghettification, torn apart atom by the differential gravitational pull. But for now, at the moment of crossing the event horizon, they are, from their internal perspective, entirely unharmed. In just a moment, you will comprehend the profound significance of this insistent emphasis. Now, I pose a pivotal question. What would you, the distant observer, witness if you were to meticulously track the astronaut's descent into the black hole through the lens of a powerful telescope? Your perception, it turns out, would be diametrically opposed to the astronaut's lived experience, a vision of absolute dissimilarity. The widely known and frequently discussed phenomenon dictates that if one observes from afar an astronaut's approach to the event horizon of a black hole, one will never, in fact, witness their actual crossing of that boundary. Instead, from your external vantage point, the astronaut would appear to move with an ever-decreasing velocity, slowing inexorably until they seem to become utterly frozen, perpetually suspended directly upon the event horizon itself, an eternal, spectral silhouette. This captivating visual distortion is a direct consequence of the extreme time dilation that occurs in the immediate vicinity of a black hole, an effect rigorously predicted by Einstein's theories of relativity. However, Susskind reveals that something far more disturbing, something that utterly defies conventional logical explanation, would also transpire. While from the astronaut's internal frame of reference they would serenely and imperceptibly traverse the event horizon, encountering no obstacles whatsoever, from the perspective of the remote observer, this very same astronaut, having approached the event horizon, would be confronted by something truly horrific, the most lethal wall of fire in the entire universe, an inferno generated by the very exotic phenomenon of Hawking radiation. And the temperature of this incandescent wall, whatever its true nature might entail, would reach an unfathomable, perhaps even infinite degree, instantly incinerating the astronaut completely. This terrifying phenomenon is known in the scientific community as the black hole firewall. Pause. Just pause for a moment. What? Did you comprehend that? You heard correctly. And the implications are staggering. We are presented with two utterly, fundamentally contradictory points of view, two irreconcilable descriptions of the identical event. On one hand, we have the astronaut's subjective perspective, wherein they calmly and unhinderedly cross the black hole's event horizon, experiencing no impediment whatsoever, continuing their descent into the unknown. On the other hand, we have the detached, external perspective of a remote observer, according to which the very same astronaut meets a horrific, agonizing demise, instantly vaporized within a searing corona of flame that encircles the event horizon. Which of these two viewpoints, then, is the correct one? This is the central, bewildering paradox. Surely, an astronaut falling into a black hole cannot simultaneously exist in a bifurcated state, both alive and, at the same instant, violently dead, annihilated by an infinitely hot barrier. Such a scenario violates every tenet of classical logic and common sense. Leonard Susskind, along with numerous other eminent physicists, posits a resolution that is as astonishing as the paradox itself. Both viewpoints are, in their respective frameworks, absolutely correct. How, you might reasonably inquire, is this to be reconciled? This profound intellectual knot is unraveled by a concept known as the principle of black hole complementarity, or additional value. This principle was originally proposed jointly by Leonard Susskind and Nobel laureate Gerard T. Hooft, two titans of theoretical physics. As Susskind himself elucidated to his colleagues, the essence of black hole complementarity lies in the bewildering, yet rigorously demonstrated, fact that, as insane as it sounds, both stories are equally true. Without a doubt, this notion clashes violently with our ingrained ordinary logic, which dictates that a person exists in one of two binary states, either alive or dead. However, Leonard Susskind assures us that there is no need for alarm or existential despair, precisely because these two radically divergent perspectives can, in fact, never be directly compared or verified against each other within a shared frame of reference. The astronaut, once having crossed the event horizon, is irrevocably trapped. They cannot escape the black hole to return and provide empirical evidence to the remote observer that they are, indeed, alive and well. Conversely, the remote observer cannot simply leap into the black hole and pursue the astronaut, attempting to confront them with the assertion of their fiery demise. This is due to the inexorable physics of time and information. The remote observer requires a finite, yet significant amount of time for the information, the light, and other radiation indicating the astronaut's fiery end, to traverse the vast distances and reach their position. Crucial mathematical calculations reveal that by the time the remote observer is able to definitively conclude that the astronaut has been incinerated, they would no longer possess sufficient time to jump into the black hole themselves and catch the astronaut, for by that point, the astronaut would have already been irrevocably consumed by the black hole's central singularity, a region where all known laws of physics as we understand them break down entirely. It is as if the very laws of physics in their intricate dance conspire to safeguard reality from the emergence of an unresolvable, self-contradictory paradox. Yet, I confess, this intellectual resolution offers little solace to my intuitive understanding, as it does nothing to diminish the sheer, mind-bending absurdity of a situation wherein two not merely different, but actively contradictory points of view are simultaneously, equally, and demonstrably valid. The objective meaning of the simultaneity of two events was lost in 1905, with Einstein's theory of special relativity, yet the very concept of an event itself remained as solid as a rock. If a nuclear reaction is occurring within the Sun, all observers, regardless of their relative motion, will unanimously agree that this event is taking place within the Sun. No observer would register it as occurring on Earth. However, within the immensely powerful gravitational field of a black hole, something entirely novel and profoundly unsettling transpires, something that undermines the very objectivity of events themselves. Events that a falling observer would perceive as having happened deep within the immense black hole are, by another observer, registered outside the horizon, dissolved and re-encoded within the noisy, shimmering curtain of photons from Hawking radiation. Leonard Susskind. This is, of course, all very peculiar, you might rightly assert. Black holes, by their very nature, are enigmatic, profoundly strange objects, points in the cosmos where our conventional understanding of physics strains and often breaks down entirely. But why, you might ask, are we even discussing these cosmic leviathans when our initial inquiry concerned an anomaly that might reveal itself only after an exceedingly long journey through space? far beyond Earth's familiar confines. The crucial insight, as articulated by Susskind, is that the extraordinary and paradoxical phenomena observed in the immediate vicinity of black holes are not isolated cosmic curiosities. Rather, they find their precise and unsettling analogues at the very boundary of our observable universe, the cosmological horizon. What is the fundamental essence of this connection? Our universe is not static. It is undergoing an accelerated expansion, effectively doubling its immense size approximately every 15 billion years. In every conceivable direction, at a distance of roughly 15 billion light-years from us, we encounter a horizon of events, eerily similar in its implications to the event horizon of a black hole. Beyond this cosmological horizon, objects are receding from us at velocities exceeding the speed of light, not because they are moving through space faster than light, but because the very fabric of space between us and them is expanding at such an accelerated rate. Consequently, any light or information originating from these regions will never, under any circumstances, be able to reach us. Thus, mirroring the behavior of a black hole, this represents a boundary of no return, beyond which objects vanish permanently from our causal connection. Given that this cosmic expansion is occurring uniformly and simultaneously across all points in space, it implies a truly remarkable and somewhat unsettling truth. Literally every one of us is encircled by our own unique cosmological horizon. This can be visualized as an immense spherical boundary, beyond which all distant celestial bodies are receding faster than the speed of light, ensuring that no signal, no fragment of information, can ever reach us from beneath this horizon. Just as with a black hole, this represents an irreversible boundary, a cosmic threshold where objects effectively disappear from our observable reality forever. At this very moment, wherever you choose to direct your gaze into the deep cosmos, at a distance of approximately 15 billion light-years, your own personal cosmological horizon is ceaselessly engulfing galaxies, swallowing stars, and quite possibly even entire civilizations and forms of life, erasing them from our empirical grasp. It is as if each of us is dwelling within our own inverted black hole, perpetually consuming the surrounding space, or perhaps, more accurately, having the surrounding space recede into an unknowable expanse. And this is not merely a charming poetic analogy. The rigorous mathematics of cosmology confirms that, as an object approaches this cosmological horizon, we, the observers, would witness phenomena strikingly similar to those at a black hole's event horizon. We would observe its motion decelerating, gradually slowing to a virtual standstill, because the light emanating from it would need to traverse ever-increasing distances due to the accelerating expansion of space, distorting its perceived velocity. And, again, mirroring the black hole scenario, if you could hypothetically dispatch a thermometer affixed to the terminus of an impossibly long and resilient cable towards the vicinity of your cosmological horizon, you would discover that the ambient temperature would progressively escalate, eventually reaching an infinite magnitude precisely at the horizon itself. If Susskind's extrapolations hold true, then at this very instant, were you to possess the ability to visually apprehend a distant planet approaching your cosmological horizon, you would perceive that planet being scorched to oblivion, incinerated in a horrifying wall of flame at the very edge of your observable universe. Yet if that planet happened to harbor intelligent sentient beings from their internal perspective, their existence would remain entirely undisturbed, in perfect order. And from their existent vantage point, it would be still they who are inexorably approaching the boundary of their cosmological horizon. And from their perspective, it is we who, at this very moment, are being consumed by that fiery inferno. How is such a mind-bending contradiction to be explained? Do not anticipate an immediate answer, for in the labyrinthine corridors of theoretical physics, some questions currently possess none. From this extended and intellectually labyrinthine narrative, Leonard Susskind and Gerard T. Hooft draw conclusions that are both far-reaching in their implications and no less shocking in their conceptual audacity. Let us revisit the central enigma. If, from the perspective of a distant observer, nothing can truly penetrate the interior of a black hole, if matter merely appears to freeze on its surface, then by what mechanism does a black hole apparently increase its volume? The perspective of a distant observer, nothing can truly penetrate the interior of a black hole. If matter merely appears to freeze on its surface, then by what mechanism does a black hole apparently increase its volume? The answer, startlingly, is that it doesn't, not in the traditional three-dimensional sense we intuitively understand. For the perceived volume of a black hole, they contend, is something akin to an illusion, a trick of our three-dimensional perception. The radical proposition is that everything that ostensibly falls inside a black hole is, in actuality, encoded upon its two-dimensional surface in the form of discrete bits of quantum information, much like the coarse, pixelated representation on a crude illustration. This concept forms the cornerstone of what is known as the holographic principle. And here lies the even more expansive, mind-bending leap. What holds true for black holes, these most extreme objects in the universe, is also posited to be true for everything else, for the entirety of reality. This is because any arbitrary region of space, any collection of matter, could, under sufficiently extreme compression, theoretically be transformed into a black hole. In essence, Susskind and T. Hooft put forth the staggering assertion that everything you currently perceive around you, the entire vivid and seemingly solid three-dimensional world, might in fact be a hologram, an intricate projection meticulously encoded on the two-dimensional, flat surface of the cosmological horizon that perpetually surrounds us. And this, crucially, is not some esoteric fringe hypothesis relegated to the margins of academic thought. The holographic principle is, at this very moment, a vigorously developing and profoundly influential area of research, actively shaping various domains of theoretical physics, offering a radically new paradigm for understanding the fundamental nature of space-time and information. The question then arises, does it feel to asterisk you as though you are merely a collection of encoded information residing on some distant, two-dimensional surface? Most certainly not. And the reason for this lack of subjective awareness is precisely analogous to why the astronaut, plunging into the black hole, does not subjectively experience being brutally smeared across a flat event horizon. Our internal perception, our conscious experience is designed, or perhaps generated, to inhabit the three-dimensional illusion. String theory, for those who are prepared to treat its intricate postulates with the intellectual gravity they demand, pushes this concept even further. It suggests that every single bit of information, whether it pertains to the state of a particle within a black hole or the precise molecular arrangement of black ink on a newspaper page, is ultimately situated and contained upon the outermost boundary of the universe itself, or, in the absence of a cosmic edge, at an effective infinity. This leads to the astonishing conclusion that Susskind and T. Hooft collaboratively arrived at. The three-dimensional world of our everyday experience, the universe teeming with galaxies, stars, planets, houses, stones, and people, is a hologram. It is an image of reality, encoded on a distant, two-dimensional surface. This new law of physics, termed the holographic principle, asserts that everything contained within a specific region of space can be fully described by bits of information located on its boundary. Leonard Susskind. Bits of information. What the devil are these? Bits of information, you might exclaim, a ripple of unease or outright disbelief spreading through your consciousness. What, in the name of all that is tangible, is this, encoding on a remote flat surface? Are we truly discussing actual physical objects, the robust, tactile world of stars, planets, and living beings? Or are we, in fact, conversing about mere computer code, abstract digital patterns, a grand algorithmic tapestry? At this juncture, it is imperative to introduce a brief but crucial interlude, a moment of reflection, and a necessary disclaimer. As this narrative unfolds, you will encounter the illustrious names of some of the most prominent and influential scientists of both the current and preceding centuries. Individuals whose intellectual prowess and groundbreaking discoveries have fundamentally reshaped our modern comprehension of the cosmos. We are together systematically progressing towards the most compelling and substantive arguments that lend credence to the simulation hypothesis. I acknowledge and anticipate that, for some, this journey might evoke a sense of trepidation, a profound existential disquiet, or even outright alarm. I often receive correspondence that reflects a range of emotions, from profound wonder to deep anxiety. Therefore, allow me to explicitly state, regardless of how persuasive or intellectually compelling the arguments presented may appear, the simulation hypothesis, thankfully, remains, at present, firmly within the realm of philosophical discourse and speculative scientific inquiry. It has not, I repeat, not yet transcended these boundaries to become an established, empirically proven fact. Please, endeavor to keep this crucial distinction firmly in mind as we continue our exploration, allowing for intellectual curiosity without succumbing to unwarranted fear. There once was a scientist, a visionary, who long before many of his contemporaries discerned that something fundamentally anomalous was occurring in the environs of black holes, phenomena that profoundly challenged the prevailing paradigms of physics. This individual, a true titan of 20th century science, contributed his intellectual might to virtually every major physical development over the past century, his influence a sprawling and pervasive force. He co-authored pivotal papers with none other than Niels Bohr, that seminal figure of quantum theory, actively participated in the epoch-defining Manhattan Project, and perhaps most significantly, cultivated an extraordinary cadre of extraordinarily talented scientific minds. Among his protégés were Hugh Everett, who first conceived the mind-bending idea of the multiverse; Kip Thorne, the astrophysical mastermind whose scientific contributions underpinned much of the cinematic science in the film Interstellar; Richard Feynman, a physicist whose brilliance and charisma were, as you undoubtedly know, truly magnificent, and countless other luminaries. Ultimately, it is to this remarkable scientist that we owe the very nomenclature we employ today. He is the one who bestowed upon these enigmatic cosmic entities the evocative, now ubiquitous, name black holes. This extraordinary scholar was known as John Archibald Wheeler. In 1998, during a seemingly innocuous lunch at the venerable Princeton University, I posed a question to Wheeler, a query concerning the future trajectory of physics. What, in his sagacious estimation, would emerge as the dominant, most critical theme in the decades that lay ahead? He inclined his head, a gesture I had observed him perform countless times that day, as if his aging skeletal structure felt the immense strain of supporting such a prodigious intellect. This time, however, the pause that followed my question extended, stretching into an uncomfortably protracted silence, which momentarily led me to doubt his willingness to respond, or perhaps even to suspect that the question itself had momentarily slipped from his prodigious memory. But then, with a deliberate slowness, he lifted his gaze, fixing it intently upon mine, and uttered a single, solitary word. A word that, in its brevity, carried the weight of profound insight. Information. Wheeler's radical proposition was that the more conventionally perceived constituents of reality, objects, matter, and radiation, ought to be re-evaluated as secondary phenomena. Instead, he argued, they should be understood as mere carriers, ephemeral manifestations of a more abstract, yet infinitely more fundamental, underlying essence, information itself. He maintained that information, encompassing the precise location of a particle, the orientation of its intrinsic spin, the polarity of its charge, whether positive or negative, and myriad other quantifiable attributes, constituted the integral, irreducible core at the very heart of reality. From this profound reorientation of perspective, our entire universe could be conceivably reimagined and understood as a colossal, self-organizing information processor. This remarkable insight is drawn directly from the pages of Brian Greene's illuminating work, The Hidden Reality, a book that meticulously explores the multifaceted landscape of our universe. Within its chapters, Greene dedicates an almost entire chapter to a rigorous and deeply contemplative exploration of the simulation hypothesis. This was, I must admit, a revelation of considerable surprise to me. And in that moment, I found myself reflecting. If even the most celebrated and globally recognized string theorist, a luminary of Brian Greene's stature, is willing to dedicate such significant intellectual energy and space to this particular idea, then who indeed am I to dismiss it out of hand, to turn up my nose at its profound implications? It was precisely this realization, this intellectual validation from such an esteemed source, that served as the pivotal point, the definitive launchpad, for my exhaustive investigation into this topic. It became clear that a surprisingly large number of distinguished scientists are, in fact, prepared to seriously entertain the notion of the universe as a computational system. It is important to clarify that this perspective does not invariably necessitate the premise of a programmer actively designing our reality. Nevertheless, the idea of a universe governed by computational principles holds significant sway. Edward Fredkin and Stephen Wolfram, for instance, are prominent advocates for the view that the universe operates as a colossal cellular automaton, a system that, through the iterative application of incredibly simple programmatic rules, is capable of generating the breathtaking complexity of observed physical phenomena. Frank Tipler, another notable figure, boldly posits that the cosmos itself is a program, albeit one existing without the need for an external tangible computer, an abstract computational process unfolding through existence. Lex Fridman, a widely respected artificial intelligence researcher and podcaster, demonstrates a profound and consistent interest in the simulation hypothesis, frequently engaging with its proponents and critics. Furthermore, Neil deGrasse Tyson, as the charismatic host of some of the world's most popular debates on this very subject, concluded one such discussion by asserting that he assigned a very high probability to the simulation hypothesis. Indeed, John Wheeler's own words resonate with particular prescience here. So, I think the probability can be very high. Is it unreasonable to imagine that information lies at the core of physics, just as it lies at the core of a computer? But how, one might reasonably inquire, did humanity initially arrive at this startling conceptual leap? The notion that our intricately structured world might, at its fundamental core, bear a resemblance to a computer, a grand computational engine. The answer lies rooted in a deeply ingrained yet often unacknowledged property of our universe, a fundamental law that inherently permits and facilitates the existence of virtual worlds. This pivotal principle is known as the Turing principle. In essence, it asserts that the underlying physics of our universe allows for the theoretical construction of an entity, a machine, an algorithm, a system, that possesses the capacity to perfectly simulate any part of our universe, irrespective of its scale or complexity. Your smartphone, for instance, or the personal computer you might be using at this very moment, are rudimentary, yet illustrative, examples of such Turing-complete objects, capable of simulating a vast array of processes. Yet, upon deeper reflection, it is far from self-evident why such a profound capability should even exist within the natural laws governing our reality. And when we speak of the physics of our world enabling the simulation of any part of the universe, we are referring to parts of potentially arbitrary size and with an arbitrarily high degree of precision. Consider, for example, the video game No Man's Sky, released in 2016. This ambitious title boasts a simulated region of a universe containing an astonishing 255 galaxies, populated by a truly mind-boggling number of planets, approximately 18.5 quintillion. Each of these planets is uniquely generated, featuring its own distinct landscape, flora, and fauna, all meticulously crafted through sophisticated procedural generation algorithms. The sheer scale is staggering. To visit just one planet per second, it would take you an estimated 585 billion years to explore them all, a duration 42 times greater than the estimated age of our entire universe. The profound significance of the Turing principle, to put it mildly, extends far beyond the realm of computer games. Indeed, without this foundational principle, not only would the existence of computers themselves be impossible, but also the emergence of sentient, thinking beings such as ourselves. For, in a very real and fundamental sense, every time you consciously observe something or engage in a complex thought process, you are, quite literally, constructing a virtual environment within the intricate neural architecture of your own brain. Should you, for example, choose to vividly imagine your childhood school, a specific portion of the universe, the complex network of neurons within your cranium is actively initiating and running a sophisticated simulation of another, geographically distinct portion of the universe, your remembered school building. Even Albert Einstein, in the arduous process of formulating his groundbreaking theories, conducted virtually all of his pivotal experiments not in a physical laboratory, but entirely within the confines of his own mind, employing, quote, experiments that allowed him to explore the very frontiers of physics without the need for elaborate physical apparatus. It was only later that these conceptual experiments, in various forms, were meticulously carried out in the real world, either confirming or refuting his brilliant hypotheses. Such mental simulation is only possible precisely because the fundamental laws governing our universe permit and facilitate the existence of internal, virtual representations of reality. Moreover, if not for the Turing principle, not only would intelligent life be absent, but indeed any form of life, even the most primitive, would be impossible. This is because the very essence of life, encapsulated within our genes, inherently involves the creation and transmission of information about the environment in which an organism exists, a process we recognize as adaptation. Present a biologist with a particular animal specimen in a laboratory setting, and with sufficient analytical tools, they can precisely and accurately deduce the environmental conditions and ecological niche the animal inhabits. Observing a fish, we immediately comprehend its aquatic dominion. A bird, the vast expanse of the sky. A monkey, the intricate canopy of trees, and so forth. Should we ever, by some extraordinary stroke of fortune, acquire a single molecule of DNA from an exoplanet in a distant star system, then, given the requisite advancement in our biotechnological capabilities, we would swiftly uncover a vast trove of information, if not everything, about that specific region of the universe from which the DNA originated, its planet, its atmospheric composition, its climatic patterns, and potentially even the broader characteristics. The very possibility of any life, in all its myriad forms across the cosmos, hinges upon the universe's inherent capacity to generate simulations of itself, to continuously reproduce, evolve, and process information. As David Deutsch, a theoretical physicist and a pioneer in the field of quantum computation, eloquently stated, life is the means by which virtual reality was first realized in nature. Thus, it appears that even prior to the advent of the very first electronic computers, certain individuals harbored an intuitive suspicion, a nascent understanding, of this simulated aspect of reality. However, it was the publication of a groundbreaking paper in 2001, authored by the Oxford professor and philosopher Nick Bostrom, titled, "Are You Living in a Computer Simulation?" that truly propelled the simulation hypothesis into the serious intellectual consciousness of the scientific community. This seminal work achieved such widespread recognition and influence that a reference to it is now almost ubiquitous, appearing in virtually every YouTube video or academic discussion devoted to the simulation hypothesis. I would be hard-pressed to identify another philosophical article that has garnered such consistent and fervent attention. While our current discourse does not afford us the luxury of a comprehensive, in-depth examination of Bostrom's intricate argument, it is essential to briefly outline its core premise. The argument, in essence, posits the following. If humanity manages to avoid self-extinction before it develops the technological capability to create sophisticated, highly realistic computer simulations of consciousness and entire universes, and, if we do not, for whatever reason, collectively impose a categorical prohibition on the creation of such simulations, then, in all probability, we are, at this very moment, residing within a simulation. This conclusion stems from a simple, albeit mind-bending statistical inference. If there exists but one truly original universe, but within that universe, billions upon billions of highly realistic simulations are subsequently created, then the statistical likelihood of any given conscious entity, such as ourselves, being born into the single unsimulated universe shrinks to an infinitesimally small probability, perhaps 1 in a billion, or even far less. This precisely is the underlying statistical reasoning that informed Elon Musk's much-quoted assertion that the probability of our existence within a simulation is 1 in a billion. However, it is crucial to resist the urge to simply roll one's eyes and dismiss this as yet another idiosyncratic pronouncement from a tech billionaire. I reiterate, Elon Musk is far from the sole intellect deeply influenced by Bostrom's provocative paper. For instance, in a rigorous article by the acclaimed astronomer and gigachad David Kipping, a meticulously calculated assessment is presented, suggesting that the current probability of our being simulated is approaching a striking 50%. Yet even this is not the most audacious estimation. Another distinguished physicist and Nobel laureate, George Smoot, goes even further, positing that we are almost certainly inhabitants of one among an uncountable multitude of simulations. He offers an estimation that dwarfs even Musk's already staggering figure, suggesting that the probability of our simulated existence could reach an astounding 1,000,000,000,000. Smoot's conviction is so strong that he delivered a captivating 20-minute TED Talk provocatively titled, "You Are in a Simulation, and Physics Can Prove It." But what profound motivations could compel a future civilization, or indeed humanity itself, to undertake the monumental task of running such a vast and intricate array of simulations? The answer, at its most fundamental, lies in the pursuit of knowledge, in scientific and philosophical inquiry. As a minimum, these would serve invaluable research purposes. Even today, scientists across diverse disciplines, physicists, biologists, Sociologists, economists, climatologists routinely employ billions of simulations running on powerful computers. Of course, these are currently crude models, highly simplified representations of reality. However, with a relentless march of computational power, these simulations will inevitably grow increasingly sophisticated, progressively mirroring the intricacies and nuances of actual reality to an indistinguishable degree. Scientists could meticulously investigate the long-term impact of life on the fundamental structure and evolution of the universe, or trace the complex pathways of biological evolution under varying conditions, or even meticulously map the rise and fall of civilizations, exploring intricate social and economic processes. As George Smoot elucidates, if you are an anthropologist or a historian, or if you want to properly understand the rise and fall of civilizations, then you will need to perform many different simulations involving millions and billions of people. This raises immediate, practical questions of scale. How gargantuan would such a computer need to be, and how long would it take to compute hundreds, thousands, or even millions of years of simulated history? Brian Greene offers a mind-bending answer. A quantum computer, no larger than a conventional laptop, would require merely a fraction of a second to simulate the entire collective thoughts, experiences, and decisions of all humanity throughout its entire recorded history. You, dear listener, bear a striking resemblance to an individual who accepts all phenomena without surprise, viewing every event as merely a fleeting fragment of a dream, implicitly believing that true awakening is imminent. Indeed, the very act of dreaming offers a perfect, compelling paradigm for connecting to a simulation. The intricate, often hyper-realistic experiences that unfold during sleep can, at times, be literally indistinguishable from waking reality, leading us to accept their vivid illusion as absolute truth. And it appears that humanity, as a collective, is rather preoccupied, perhaps even obsessed, with the imperative of prolonging our waking hours, of postponing our descent into the realm of Morpheus for as long as humanly possible, clinging fiercely to our perceived real world. The famed Fermi Paradox, which eloquently poses the question, "Where is everybody?" is frequently invoked as a compelling piece of circumstantial evidence in favor of the simulation hypothesis. It highlights the perplexing observation that the cosmos, despite its unimaginable vastness and the sheer statistical probability of extraterrestrial life, appears to us as a desolate, empty stage, seemingly populated by only ourselves, as if this grand cosmic theater was constructed for a singular audience of one. However, it is highly probable that this paradox can be resolved through a far simpler explanation. When robust evidence supporting the Big Bang theory began to accumulate, conclusively establishing the universe's age at approximately 13.8 billion years, it generated a significant degree of consternation among certain biologists. Their prior assumption had often been that life, across the cosmic expanse, possessed an effectively infinite past during which to spontaneously arise and evolve. The notion that complex living organisms could emerge and diversify within such a relatively constrained time frame seemed, to many, implausibly rapid. Indeed, all probabilistic calculations concerning abiogenesis, the spontaneous generation of life from non-living matter, strongly suggest that even billions of years is an astonishingly brief period for the improbable genesis of life. This becomes even more pronounced when considering the emergence of consciousness, a phenomenon whose prerequisite conditions and developmental pathways remain profoundly unclear and enigmatic. However, the apparent constraint of limited time finds its compensatory counterpart in the immense, often infinite, expanse of space. Across these boundless cosmic frontiers, any event, no matter how astronomically improbable, is destined to occur an infinite number of times. Therefore, the implication is that we are likely not the sole sentient beings in the universe. Rather, other intelligent species, owing to the extreme rarity and improbable nature of life's genesis, may simply be situated at such colossal distances from Earth that their light, or any other form of signal, would never, throughout the entire lifespan of the cosmos, be able to traverse the gulf and reach us. But what if this common resolution is in fact incorrect? What if we truly unique, truly alone? What if we are indeed residing within a simulation, and the cosmos, contrary to popular scientific belief, is not infinite? For a truly infinite universe, in its boundless and ceaseless complexity, would be an impossible computational burden to simulate with any degree of fidelity. The very concept of rendering an infinite number of details and interactions defies the inherent limitations of any finite computational system. So, then, how might a universe that is both flat, as observational data suggests, yet simultaneously finite manifest itself? Would we, at some eventual point, simply collide with an invisible barrier, a digital wall beyond which nothing exists? Such imagery, I assure you, fails to capture the intricate reality. Our conventional imagination, bound by 3 Euclidean dimensions, is simply inadequate to conceive of such a structure. Indeed, it required the immense processing power of a modern supercomputer to calculate and visualize what a flat, yet non-infinite universe might actually look like. And the answer, as we shall see, is profoundly, unsettlingly unusual. Our journey into this conceptual space must begin with a seemingly innocuous, yet illustrative, detour. Recall the classic arcade game Pac-Man. In this two-dimensional digital realm, traversing beyond the rightmost edge of the screen instantly transported your character to the leftmost extremity of the map. Similarly, exiting at the top of the screen immediately brought you back into play from the bottom. In this ingenious design, the game's space, though distinctly flat, effectively looped back upon itself. If one were to attempt to embed this two-dimensional Pac-Man universe into our familiar three-dimensional space, conceptually connecting its left and right boundaries and its top and bottom boundaries, the resulting geometric form would be that of a torus, colloquially known as a donut or a bagel. Crucially, the internal geometry of this space would remain flat. Parallel lines would never converge or diverge, and the angles within any triangle would always sum to 180 degrees, adhering perfectly to Euclidean principles. However, a critical challenge arises in this straightforward visualization. In order to physically connect these edges within a visible three-dimensional embedding, as depicted in any simple animation, the two-dimensional surface would necessarily need to be stretched and distorted. Such a distortion would, for instance, lead to a situation where the fundamental laws of physics would manifest differently depending on the direction of travel, an anisotropy that contradicts our empirical observations of the universe. In our observed cosmos, we perceive no such directional preference. All directions in space appear to be equivalent, and the laws of physics operate uniformly irrespective of orientation. Therefore, if our universe is indeed flat yet simultaneously closed and finite, its actual topological structure would be far more intricate and mind-bendingly phantasmagoric than a simple donut shape. Do you recall the film A Beautiful Mind, which chronicled the extraordinary life of the brilliant mathematician and Nobel laureate John Nash? In one poignant scene, a character questions, "Is the universe vast?" The reply, "Infinitely." "How do you know?" "All the data points to it." But it's not proven, is it? No. Have you seen it yourself? Then how can you be sure? Well, John Nash, through his profound mathematical genius, rigorously demonstrated that it is possible to isometrically embed a flat torus into three-dimensional space, meaning to embed it without altering the intrinsic distances between any of its points, preserving its flatness. While the mathematical proof existed, the actual visual manifestation of such a shape remained utterly inconceivable to the human mind. However, leveraging the immense computational power of a supercomputer, a team of French scientists in 2012 succeeded in calculating and visualizing what this hitherto unimaginable form would look like. In essence, the Pac-Man universe, embedded without distortion into three-dimensional space, would present itself in a configuration far more complex than a simple torus, appearing as a structure that, to our senses, would defy easy description, perhaps resembling a higher dimensional projection. And it is entirely plausible, indeed quite likely, that our own universe possesses a similar complex topological structure, specifically designed to instill in us the powerful yet potentially misleading impression that it is infinitely vast and boundless. If this were the case, if our universe were indeed a flat yet finite space with such a complex topology, then a deep, penetrating gaze into the distant cosmos might reveal a startling truth. We might, for example, eventually discern that an exceedingly remote galaxy, seemingly light years beyond our own, is in fact none other than our very own Milky Way galaxy. The light, having traversed the immense, self-intersecting expanse of a closed universe, would have simply completed a grand loop, returning to us from another direction, an echo of our cosmic home resonating across time and space. While current observational data does not definitively confirm such a phenomenon, we have not yet observed such cosmic self-portraits. This absence of evidence is, in itself, not entirely surprising. For if our universe were to possess artificial seams, these structural boundaries would, by design, be strategically placed well beyond the limits of the observable universe, in regions from which light could never reach us. This ingenious arrangement would effectively preserve the powerful illusion of an infinite, seamlessly continuous cosmos, ensuring that its inhabitants remain unaware of its true, bounded nature. As Brian Greene astutely observes, simulated individuals dwelling on a simulated Earth would experience no sense of confinement or boredom if the underlying computer merely rendered and modeled the portion of the universe contained within their local cosmic horizon, allocating resources only to what is immediately relevant to their perception and experience. However, our focus should not be confined solely to the grand, distant cosmic scale. It is equally imperative to scrutinize what lies directly before our very noses, to delve into the microscopic and submicroscopic realms. If we are indeed situated within a simulation, and if, as is logically necessitated by any computational system, the resources of the simulating computer are inherently finite, then it follows that everything we perceive, when magnified to a sufficiently extreme degree, must ultimately prove to be discrete rather than continuous. In other words, at its most fundamental level, reality would have to be composed of a finite number of distinct points, akin to the pixels on a digital display. This immediately brings to mind the compelling analogy of virtual reality goggles. While the virtual world projected before our eyes appears seamlessly continuous and immersive, a close, focused inspection will inevitably reveal the underlying pixel grid, a subtle, almost imperceptible tessellation that betrays the digital nature of the image. And this, precisely, is where the intrigue deepens. Brian Greene, along with many other leading physicists, posits that the world, at its most fundamental and irreducible level, is indeed discrete, Thus, within the framework of the simulation hypothesis, this profound discreteness could signify that space-time itself, the very fabric of our existence, is not a smooth, continuous manifold, but rather a colossal pixelated lattice, a vast, three-dimensional grid of fundamental units. I was particularly captivated by the elegant manner in which this concept was elucidated by a programmer named Alex Gusev in his article on Habra, a technique that he masterfully employs through the lens of Zeno's paradoxes. Zeno of Elea, an ancient Greek philosopher, famously argued that a flying arrow is, in actual fact, perpetually motionless. His reasoning was thus: at any given, infinitesimally brief moment in time, the arrow occupies a specific, static position, and therefore, it is at rest. Since it is at rest at every individual moment in time, it logically follows that the arrow must be at rest at all times, and thus, its motion is an illusion. Now, let us apply this ancient paradox to our modern hypothesis. If spacetime is indeed composed of such distinct, indivisible pieces or pixels, then, upon applying an incredibly powerful, near-infinite magnification, we would not observe a smooth, continuous transition from one position of the arrow to the next. Instead, we would witness an instantaneous, abrupt jump, a teleportation, from one pixel of spacetime to an adjacent one. Crucially, in the infinitesimally small interval between these discrete jumps, absolutely nothing would exist. The arrow would not be in any intermediate state. And at each subsequent moment in time, the arrow would again be found to be perfectly still, residing motionless within a single pixel. Consider an analogy found to be perfectly still, residing motionless within a single pixel. Consider an analogy from the realm of computing. How much time does an arithmetic shift operation take within a processor? 1 clock cycle. What, from the perspective of the shift operation itself, exists between these clock cycles? Nothing. The operation is either in one state or the next. And what occurs during the clock cycle? From the perspective of the operation, again, nothing in terms of continuous transition. It's a discrete state. The apparent uniformity and continuity of motion that we perceive in the real world could, therefore, be a sophisticated illusion, much like the illusion of continuous movement created in a cinematic film, where a rapid succession of discrete, static images, individual frames, is presented to the eye, giving the impression of fluid motion. In video games, this concept is quantified as FPS, or frames per second. What truly exists between these individual frames? Nothing. The more powerful the computer's hardware, the greater the number of frames per second it can render. Yet, the number of frames, no matter how high, always remains finite. For a comfortable gaming experience, approximately 30 FPS is generally deemed sufficient. If you were to employ a high-speed camera, recording at thousands of frames per second, then upon playing back the footage in slow motion, you would effortlessly observe that, instead of continuous, fluid movement, you are witnessing a rapid sequence of distinct, static frames. However, as the eminent Russian theoretical physicist Igor Ivanov notes in his lecture, Journey into the Depths of a Second, with dedicated training, a human being can, with the naked eye, distinguish individual frames even at an astonishing rate of 3,000 frames per second. Bringing this back to our larger hypothesis, the movement of objects in our perceived reality might literally be instantiated by the process of quantum particles disappearing from one point and instantaneously reappearing at another, a fundamental form of digital rendering. Zoe Davudi, a theoretical physicist at the Massachusetts Institute of Technology, along with her esteemed colleagues, has gone so far as to propose a concrete experiment designed to test this very hypothesis. the idea that our universe might be fundamentally discrete, we hypothesized that an experiment could potentially uncover indications of an underlying simulation governing the universe. Space, to our macroscopic senses, certainly appears continuous. However, we have only rigorously tested this continuity down to distances no smaller than a billionth of a meter. It remains a distinct possibility that, with even more precise and sensitive equipment in the future, we might ultimately establish that space is fundamentally discrete at its most irreducible level. But for now, this profound question remains open, awaiting further empirical exploration. A similar, constrained understanding also pertains to the very nature of time intervals. Our perception of temporal flow might also be an emergent property of a discrete, underlying structure. Furthermore, discoveries indicating that the information capacity of any region of space is precisely defined by 1 bit per unit of Planck area are pivotal steps towards acknowledging this inherent discreteness. Regardless of whether truly intelligent simulations ever come into being, I believe that we will indeed converge on the consensus that this world is fundamentally discrete. Brian Greene. This naturally leads to a provocative, indeed logical follow-up question. What then is the FPS, the frame rate per second of our ultimate reality? And it is precisely at this juncture that profound suspicions begin to surface, not just among specialized physicists, but among a far wider audience, including those quite distant from the rigorous pursuit of scientific inquiry. 299, 792, 458 meters per second. This numerical value represents the maximal possible speed within our universe. It is simply a historical convention that we refer to this constant as the speed of light. In its most fundamental essence, however, it represents the absolute, unbreakable speed limit for any interaction, most transfer of information or energy, within the entirety of our cosmos. Now consider this for a moment. We, who consume content such as this, have become accustomed to the widely accepted truth that the speed of light is an insurmountable barrier, an absolute maximum that cannot be exceeded. But endeavor to recall your initial, visceral reaction upon first learning of this concept. I, in my childhood, found it deeply perplexing, almost absurd. A seemingly arbitrary restriction plucked from thin air. Intuitively, it simply defied understanding why anything should inherently prevent an object from accelerating to an infinite speed. Even today, many individuals tirelessly devise ingenious thought experiments, attempting to conceptualize scenarios that might circumvent this absolute limit. Yet, the profound question remains, why is this specific speed limit precisely what it is? This particular value, this exact numerical constant, does not, through any known method, inherently derive from or emerge logically from the fundamental, underlying laws of physics as we currently comprehend them. It stands, instead, as yet another enigmatic artifact, one of the greatest and most persistent mysteries confronting contemporary physics. However, from the perspective of the simulation hypothesis, the speed of light finds an exceedingly elegant and straightforward explanation. It can be readily interpreted as a computational limit, a hard ceiling that directly corresponds to the maximum clock speed or processing rate of the central processing unit, the cosmic computer, upon which our entire universe is being simulated. When we, as ordinary individuals, encounter the pronouncements that the speed of light cannot be surpassed, that it remains an immutable constant, we typically fail to grasp the profound, counterintuitive strangeness embedded within this fundamental truth. Let us conduct another thought experiment to fully appreciate this anomaly. Imagine yourself suspended effortlessly in the vacuum of space, somewhere in the celestial neighborhood of Earth. You then activate a standard flashlight and, meticulously measuring the speed of the light emanating from it, you obtain the value of 299, 792, 458 meters per second. No surprises there. The result is entirely consistent with established physics. Now, let us introduce a dynamic element. Visualize Elon Musk hurtling past you in his high-performance Tesla, traveling at an astonishing 99% of the speed of light. As he zips by, he too switches on his headlights. What numerical value would he, from his own rapidly moving frame of reference, obtain if he were to measure the speed of the light emitted from his headlights? As perplexing as it sounds, despite his near-light speed velocity, he would, precisely like you, register the asterisk exact same 299, 792, 458 meters per second, no more, no less. Now, hold on a moment. This implies that if Musk, in his Tesla, flashed his lights precisely as he passed your stationary position, then the light emanating from his vehicle would travel almost twice the speed of the light from your flashlight, relative to you. This thought alone is enough to send one's mind reeling, shattering all conventional intuition. But no, that is precisely the point. This speed of light in a vacuum is an absolute constant, which means it remains identical for all observers, irrespective of their relative motion. Therefore, both for you, the stationary observer, and for Musk, the observer hurtling in his Tesla, the measured speed of light would be precisely the same. How, then, can such a seemingly impossible contradiction be resolved? The resolution lies deep within the intricate tapestry of Albert Einstein's special theory of relativity. The core of the matter is this. Due to the profound relativistic effects, and simplifying some of the more intricate nuances for clarity, the passage of time for a moving object becomes slower from the perspective of a stationary observer. Let us consider the immense distance that light traverses in a single second. Precisely 299, 792, 458 meters. If, at the exact moment, Elon Musk's Tesla drew level with your stationary position, both of you were to simultaneously activate your light sources and begin measuring your respective light seconds. The distance light travels in 1 second according to your own clock. You, the stationary observer, would complete your measurements sooner. This is because, from your vantage point, Elon Musk's time is running more slowly. Consequently, your light second, the distance light, travels in 1 of your seconds, and Musk's light second, the distance light, travels in 1 of his seconds, would indeed be different in terms of your common external measurement. If Elon Musk were to eventually return to you to compare timepieces, you would discover that his clock had, in fact, registered a shorter duration than yours, and indeed, shorter than all clocks on Earth, above which you had been freely suspended. This, despite the fact that, from Musk's own internal perspective during his flight, his clock appeared to function entirely normally, without any perceived slowing. I understand this concept is profoundly counterintuitive, likely causing your brain to swell with the sheer weight of it. Therefore, for the purpose of this discussion, you need only retain one crucial piece of information from this elaborate explanation. For objects in motion, time itself slows down. And while that concept is indeed profoundly strange, it is arguably not as strange as its companion effect. From the perspective of an object in motion, the entirety of space in the direction of its travel becomes shorter, contracting itself. And the higher the velocity, the more pronounced this compression of distance becomes. This astonishing phenomenon is known as Lorentz contraction. For instance, were you to travel at half the speed of light, the space in your direction of motion would contract by approximately 13.5%. This might sound like the stuff of outlandish science fiction, utterly implausible to our everyday experience, yet it is an absolutely real, rigorously verified, and experimentally confirmed effect of special relativity. To grasp its mind-bending scale, consider this. Once humanity masters the ability to accelerate spacecraft to half the speed of light, the perceived distance to Proxima Centauri, our closest stellar neighbor, would shrink by a staggering 5.5 trillion kilometers, plummeting from its actual 4.2 light-years to a mere 3.6 light-years. No, truly, pause and ponder this for a moment. The entire expanse of the universe literally contracts in your direction of motion when you are in transit. Let me repeat, for emphasis, for the final time, I promise. The entire universe itself compresses in the direction of your movement, even when you are merely walking to the grocery store, albeit to an imperceptible degree at such pedestrian speeds. At such low velocities, the effect is, of course, exceedingly difficult to register with current instrumentation, but the fundamental principle remains. How, then, can such a concept possibly be reconciled with our innate understanding of space? Soon, the ultimate implication of these phenomena will become abundantly clear, but for now, allow me to present one more extreme example to further solidify your understanding. If you were to travel at a velocity so infinitesimally close to the speed of light that it differed by only a minuscule fraction of a percent, the apparent distance to Proxima Centauri would, from your relativistic perspective, shrink from its objective 4.2 light-years to an astonishingly mere 1,338 kilometers. Furthermore, you would traverse this shrunken distance in a mere 20 milliseconds, while for observers comfortably situated on Earth, more than 4 full years would have elapsed. And it is precisely here that the expansive domain for compelling speculation unfolds. If our perceived reality is, in fact, a virtual construct, a sophisticated simulation, then the immutable limitation of the speed of light and all the seemingly schizophrenic phenomena associated with the compression of space find a remarkably straightforward and elegant explanation. In order to accurately calculate the trajectories and interactions of objects moving at incredibly high velocities, the underlying computer running the simulation would be compelled to execute a significantly greater volume of computations. However, if the computational resources of this simulated universe are, as is logically necessary for any finite system, inherently limited, then it can only allocate a fixed, predetermined amount of processing power to all objects within the universe, regardless of their individual speed. I spent a considerable amount of time contemplating a suitable analogy for this concept, searching for an illustrative parallel from our own technological realm. And this is the example that ultimately crystallized in my mind. In a high-fidelity racing simulator game, the computer dedicates the vast majority of its computational resources to meticulously modeling the player's immediate vehicle and its direct surroundings, rendering intricate textures, complex physics models, and dynamic environmental effects with exquisite detail. However, if the computer were instead forced to distribute its limited resources uniformly across the entire simulated world, attempting to render every blade of grass, every distant cloud, every non-player character with equal fidelity, even when they are far from the player's focus, then it would rapidly lack the necessary processing power to smoothly and continuously model the rapidly moving player's car. The car, from an external perspective, would begin to lag, its movement becoming jerky, discontinuous, and visually jarring, manifesting as a series of sudden jumps rather than fluid motion. Or, to express this in the terminology of relativity theory, from an outside viewpoint, the car's internal clock would appear to be dramatically slowed. However, the crucial question then becomes, How would this lag or slowdown be experienced from the first-person perspective of the driver within the game? Would the driver subjectively perceive their own reality to be lagging? Evidently no. This is because the driver's own perception, their entire subjective experience, is also being simulated by the computer. The driver cannot consciously apprehend the moments or intervals during which the computer is not allocating resources to render their conscious awareness. In short, from the driver's internal point of view, time would appear to flow absolutely continuously, seamlessly, and without interruption, and in such a scenario, they would perceive a world that looks precisely like this. A world where distances ahead are shortened, and where the outside world's clocks run faster. As you can see, from the driver's perspective, a literal contraction of distance occurs, and their internal time appears to flow more slowly when observed by objects that are stationary relative to them. Yet to the driver themselves, their own passage of time seems perfectly normal and unaffected. This is analogous to our earlier discussion of Zeno's arrow. If the computer simulating the arrow were unable to model it at every infinitesimally small point in spacetime, instead skipping several points at once, the arrow would still appear to be in continuous motion from a macroscopic perspective. In our actual reality, of course, everything manifests in a far more smooth and seamless fashion, devoid of perceptible glitches. However, it is entirely plausible that this perceived continuity is merely a function of the current imperfection of our modern measuring instruments, which may not yet possess the sensitivity to detect the discrete, pixelated nature of reality at its most fundamental level. As mind-boggling as these concepts may seem, there exists an even more audacious and profound idea, one intimately linked to the inherent limitations of the computational resources of the simulation in which we are potentially embedded. I regard consciousness as fundamental. I regard matter as derivative from consciousness. These words, spoken by Max Planck, one of the founding fathers of quantum mechanics and a Nobel laureate, resonate with immense weight, piercing directly to the heart of this entire discussion. One might reasonably argue that even if the universe were indeed finite rather than infinite, composed of a quantifiable, limited number of fundamental points, and even if the laws governing this universe inherently preclude anything from traveling at infinite speeds, there would still appear to be an overwhelming, perhaps even gratuitous, degree of unnecessary complexity in the world. Such an abundance of intricate detail would surely make it an insurmountable task to simulate it in its entirety, without recourse to significant compromises and optimizations. In the realm of video games, a common and essential strategy for preventing system overload and ensuring smooth performance is to avoid modeling or rendering the entirety of the vast game world at all times. Instead, objects and environments lying outside the player's immediate field of vision are not rendered in full detail until the player specifically directs their attention towards them. This technique is known as frustum culling and level of detail (LOD) rendering. Brian Greene extrapolates this concept to our potential cosmic simulation, suggesting that, for instance, the simulation might only render the stars surrounding our sun during the night, and even then, only when the sky is clear of clouds. That is, only when they are directly observable by a conscious entity. The same principle, he argues, could logically apply to the microscopic and submicroscopic realms of simulated cells, molecules, and atoms. For the most part, these intricate structures would only need to be fully rendered and calculated when they become the direct object of study for simulated specialists within a particular scientific discipline. It is only when these simulated scientists actively and directly investigate these exotic, unseen worlds, peering through simulated electron microscopes or conducting simulated particle physics experiments that the underlying computer needs to allocate the necessary resources to render their precise states and interactions. Brian Greene. And while this notion might initially evoke images reminiscent of a psychiatric ward, a suggestion of madness, I must emphasize that such ideas possess a surprisingly robust theoretical foundation. Everyone recalls, or has at least heard a simplified account of, the infamous double-slit experiment, a cornerstone of quantum mechanics that profoundly challenges our classical intuition, if not a brief and simplified descriptions. However, if no attempt is made to observe or measure the photon's path, if it is allowed to propagate unperturbed, then an entirely different pattern emerges on the screen, a complex interference pattern, characteristic of a wave. This wave-like behavior, this interference pattern, is possible only under one extraordinary condition: if the photon, when unobserved, does not possess a definite singular trajectory, but rather propagates as a mathematical wave of probability, exploring all possible paths simultaneously, existing in a state of quantum superposition. It is this fundamental observer effect that lies at the heart of quantum strangeness. Building upon this, John Wheeler proposed an even more extreme, mind-bending version of this experiment, one that stretches the implications of quantum observation to cosmic scales. Now, gaze upon these two luminous objects captured in a distant image from the Hubble Space Telescope. These are quasars, extraordinarily bright, active galactic nuclei, powered by supermassive black holes at the centers of galaxies, voraciously consuming surrounding matter and emitting immense quantities of energy. The light from these two apparently distinct quasars has journeyed through the cosmos for an astonishing period of approximately 9 billion years to reach our telescopes here on Earth. The startling truth, however, is that these are not, in fact, two separate objects. They are a single quasar. The illusion of duality arises because roughly halfway between this quasar and Earth lies a colossal galaxy cluster, possessing such an immense gravitational mass that it visibly distorts and magnifies the space around it, acting as a colossal gravitational lens. Consequently, photons of light emitted from the singular quasar have two primary paths to circumvent this gargantuan lensing galaxy. They can bend around it either via a left-hand trajectory or a right-hand trajectory. Thus, a photon, having originated from the quasar, must, in essence, choose to pass either to the left or to the right of the lensing galaxy, much like in the double-slit experiment, but on a truly galactic scale spanning billions of light-years. If we, here on Earth, were to install a highly sensitive instrument capable of precisely measuring the photons emitted by the quasar, and beyond this instrument, position a screen, then on that screen we would accurately register whether each photon passed to the left or to the right of the galaxy. This would manifest as two distinct bands on the screen, mirroring the result of the double-slit experiment. However, if we were to deactivate the measuring instrument, refraining from any observation, then the screen would, once again, display an interference pattern. This interference pattern is possible only under one extraordinary condition. Correctly, if the photon, over its 9 billion-year journey, did not possess a definite, singular trajectory, but rather traveled as a wave of probability. Let that sink in deeply. Have you truly grasped the profound implications of what is occurring in this cosmic experiment? Ponder it. The simple act of whether you choose to activate your measuring instrument here and now, in the present, retroactively determines the distant past of that photon. Because if you choose not to activate the measuring device, in other words, If you choose not to perform an observation on the photon, then it is revealed that the photon, throughout its billions of years of travel, possessed no definite trajectory whatsoever. It remained a wave of probability. If, however, you do decide to observe the photon, it instantaneously collapses into a definite state, choosing a specific, singular path. Your actions, here and now, in this precise moment, directly influence and determine whether that photon veered left or right billions of years ago, at a time when Earth was still a molten primordial sphere, devoid of even the most rudimentary forms of life. This mind-bending phenomenon is known as Wheeler's delayed choice experiment. It has been repeatedly conducted in laboratory settings on a smaller scale, with results consistently confirming its astonishing predictions. The experiment profoundly underscores a radical truth. At the most fundamental level of reality, the process of measurement does not merely register a pre-existing state. It actively forms it, bringing it into being. Reflecting on the profound implications of this experiment, John Wheeler formulated what he termed the participatory anthropic principle. According to this principle, neither the photons from the distant quasar, nor the quasar itself, nor indeed the entire universe, acquires the status of definitive, objective reality without the active participation of an observer, a conscious act of measurement or awareness. In a seminal work presented to commemorate Einstein's centenary, titled Beyond the Black Hole, John Wheeler schematically depicted the universe in a striking manner, as the English letter U, with an I positioned at one end, symbolizing the observer. The accompanying inscription, in my best attempt at translation, reads as follows: The universe is viewed as a self-exciting circuit. Starting from small beginnings, it grows, and in time, it brings forth an observer-participant, which in turn gives tangible reality even to the earliest days of the universe. And, as proponents of the simulation hypothesis eagerly point out, this concept bears a striking resemblance to the way virtual worlds are rendered in video games. The surrounding reality, with all its intricate detail, often comes into being, or is drawn, only when the player directs their gaze towards it, thereby optimizing computational resources by not rendering what is not being observed. In this framework, a computationally less expensive, yet perceptually adequate, copy of familiar reality, which then increases its level of detail and simulation fidelity only as necessitated by observation, would be entirely sufficient to create the illusion of a fully formed, continuous world. Brian Greene. Wheeler's radical perspective was echoed by another renowned theoretical physicist, Eugene Wigner, a recipient of numerous accolades, including the Nobel Prize. Wigner, too, grappling with the inherent strangeness of the quantum world, postulated that consciousness played a pivotal, indispensable role in the very formation of objective reality, in how the universe itself solidifies from probabilities into definite states. This interpretation of quantum mechanics has since been dubbed the von Neumann-Wigner interpretation. And if one were to accept this interpretation as a valid description of reality, then the startling notion that the universe is literally being drawn or rendered before our very eyes, moment by moment, would cease to appear as wildly improbable or insane. Consider the implications for computational efficiency. The microscopic structure of the Earth's interior could easily be omitted from detailed simulation. Remote astronomical objects could be subjected to an extremely high level of data compression, or even entirely de-rendered. The precise fidelity of the simulation would only need to be maintained within a narrow range of properties that we, the simulated inhabitants, can observe from our planet or from a spacecraft within the solar system. On the Earth's surface, macroscopic objects within inhabited areas might require continuous modeling to maintain their consistency, but microscopic phenomena could be instantiated ad hoc, that is, generated only as and when necessary. What you observe through an electron microscope need not inherently arouse suspicion, as you would typically lack the means to confirm its consistency with the unobserved or unrendered portions of the microscopic world. Nick Bostrom. One might, yet again, be tempted to interject, "Oh, but what does it matter?" Even with all these clever optimizations and limitations, creating a simulated universe as vast and complex as our own would still be extraordinarily difficult, perhaps even fundamentally impossible. But what if, once more, this intuition is mistaken? Stephen Wolfram, for example, a visionary computer scientist and physicist, champions the idea that the entirety of the observed complexity of the universe could, in principle, be generated from a mere handful of exceptionally simple programmatic rules or equations, akin to a minimal, elegant code. Max Tegmark, echoing this sentiment, writes that the fundamental equations governing the universe might be astonishingly simple, far more so than we currently imagine. Moreover, the ingenious computer scientist Jürgen Schmidhuber arrived at a counterintuitive realization. It is, in fact, computationally easier to program a computer to generate possible computable universes simultaneously than it is to individually program computers to create them one by one, each with its specific parameters. This seems paradoxical, yet it stems from a profound insight into algorithmic compression. To illustrate this astonishing principle, let us consider a more accessible analogy. How immensely difficult would it be to compose a single masterpiece of world literature, a sprawling epic like War and Peace, or a dense modernist novel like Ulysses? It would demand extraordinary genius, unparalleled dedication, and immense creative effort, an undertaking of monumental difficulty. Now, consider a far more ambitious, seemingly impossible task. How difficult would it be to write all possible masterpieces of world literature that have ever existed, that currently exist, or that ever will exist throughout the entire sweep of human history? Intuitively, this seems infinitely harder, but in reality, from a computational and combinatorial perspective, it becomes paradoxically much simpler. In 1941, the visionary Argentine writer Jorge Luis Borges penned a short story titled The Library of Babel, a narrative that describes an immense, perhaps infinite library. This library is comprised of hexagonal rooms, each containing 20 shelves, and on each shelf, 32 books of uniform format. Each book, in turn, contains 410 pages, with 40 lines per page, and approximately 80 black letters per line. The crucial constraint: only 25 orthographical symbols are permitted, 22 letters, a period, a comma, and a space. Digits and uppercase letters are conspicuously absent. You might ask, what is the profound point of such a meticulous, yet seemingly arbitrary, construction? The essence lies in this. This library, by its very design, contains every conceivable book with every possible combination of these 25 symbols. This immediately implies that the vast majority of these books are utterly meaningless, representing nothing more than a combinatorial brute force permutation of all possible sequences of the allowed 25 characters. However, a fundamental rule of the library dictates that no two books are identical. Therefore, the total number of books within the library, while unimaginably vast, is not infinite. It amounts to 25 raised to the power of 1/312,000. This staggering figure is often referred to as Borges's number. And while the percentage of genuinely meaningful, coherent books within this colossal collection is infinitesimally small, those meaningful books collectively encompass absolutely every text that humanity has ever created, every text it will ever create, and indeed, every text it will never create, including complete, detailed histories of all possible future civilizations, every scientific discovery, every philosophical treatise, every... As for the sheer physical dimensions of the Library of Babel, its hypothetical volume would exceed the total volume of our entire observable universe by an astronomical factor, approximately 10 raised to the power of 611, 338. Of course, such a library, in a physical sense, could not possibly exist. Yet, astonishingly, something remarkably similar, namuscodere, exists in a digital reality. Consider this. There is a website, aptly named the Library of Babel, which was meticulously created by the writer and programmer Jonathan Basile, directly inspired by Borges's story. This digital library, to a remarkable degree, simulates Borges's vision. It hosts a number of books equivalent to 10 raised to the power of 677. This number is so astronomically vast that I couldn't even fully display it on the screen. It's a 1 followed by 677 zeros. To put this in perspective, our entire observable universe contains only approximately 10 to the power of 80 atoms. If you haven't yet grasped the profound significance of my recounting this, then I urge patience. On the website, one can either manually browse through randomly generated books, or, more powerfully, one can input any text of up to 200 characters, composed of Latin letters, periods, commas, and spaces. The site's algorithm will then instantly calculate and display the precise coordinates of that text within the library, specifying the exact room, shelf, book, and page where your inputted text resides, perfectly encoded amidst the unquantifiable noise. More recently, a 3D simulation of the Library of Babel has also been created, offering a more immersive experience. Wandering through its endless, dimly lit hexagonal chambers evokes a profoundly mixed array of emotions. You are acutely aware that within these silent, dusty shelves reside all the burned pages of the second volume of Gogol's Dead Souls, a monumental work upon which he toiled for a decade. Here, too, are the final whispered words of Einstein, uttered to a nurse just before his death, words she could not comprehend or recall because she did not speak German. Scattered across countless shelves are the most granular, unsparing biographies of every human being who has ever lived, and every single person yet to be born, replete with every intimate detail, every secret, every dirty particular. At any given moment, you might stumble upon the precise formula for a cure for any known form of cancer, or a remedy for any future ailment. And somewhere, within one of these countless labyrinthine rooms, lies a book containing the genuine, irrefutable formula for immortality itself. The library holds every single thought you have ever conceived, here and there, tantalizing fragments of code for Half-Life 3-inches, a game that will likely never see the light of day, gather dust on shelves. Other tomes, perhaps millennia old, contain the unified theory of everything that scientists have fruitlessly pursued for nearly a century, or, conversely, volumes explaining precisely why such a theory is fundamentally impossible to construct. If one were to search diligently enough, literally anything expressible through the Latin alphabet, periods, commas, and spaces could be found here. Even this very paragraph you are now hearing, once transcribed into Latin characters, exists within its digital depths. Indeed, you could, right now, input these very coordinates and locate this specific passage from my script. And in a profound sense, it was already there, existing conceptually, 10 years before I ever conceived or wrote it, from the very moment this website came into being. This notion, the pre-existence of all possible information, is undeniably unsettling, even a little chilling. So, to what ultimate purpose am I recounting this elaborate tale of a boundless, combinatorial library? The crux of the matter is this. The entirety of the mind-boggling complexity within the simulated Library of Babel is generated not by individually authoring each book, but by a comparatively simple, elegant algorithm. By powerful analogy, our own universe, in all its astonishing complexity, could be but one among an innumerable multitude of other computable universes. And all of these diverse worlds, with their unique physical laws and histories, could potentially be generated by a remarkably short, compact computer code, an underlying generative algorithm. Brian Greene, in his illuminating work, acknowledges and even entertains such a variant of the matrix within his own conceptual framework. Such meticulously modeled or simulated worlds would indeed compellingly corroborate Wheeler's profound assertion regarding the primacy of information. As Greene eloquently states, create circuits that carry the correct information, and you create parallel realities that are just as real for their inhabitants as our reality is for us. These simulations I will call the modeled multiverse. However, within the intricate tapestry of our own world, there exists an anomaly, an artifact, which, in my estimation, more profoundly than any of the aforementioned phenomena, compels us to seriously contemplate the possibility of our existence within a simulation. This is the persistent mystery of galactic rotation curves. Observations of the rotational velocities of stars and gas within galaxies consistently indicate that these galaxies, based solely on their visible matter, should not, in fact, be stable structures at all. All conventional models of galactic dynamics, derived from the visible distribution of mass, dictate that there is simply insufficient gravitational force to bind the stars to their orbits. They ought, quite simply, to be flung outwards into the vast emptiness of intergalactic space. And the core of the problem is not a minor discrepancy. The visible mass accounts for only a fraction of the gravitational force required. To maintain their observed rotational stability, galaxies demand an astonishing 500% to 600% more mass than what we can currently detect. In simpler terms, instead of observing the stable, majestic spiral arms and coherent structures that characterize galaxies, we should, based on visible matter alone, be witnessing a chaotic, rapidly dispersing cloud of stars and gas. From this profound observational deficit, scientists have drawn a seemingly logical, yet ultimately deeply unsatisfying conclusion. This enormous quantity of additional, unseen mass must be generated by hitherto undiscovered particles, collectively dubbed dark matter. Yet this designation, dark matter, functions less as a genuine explanation and more as a conceptual placeholder, a linguistic stopgap to soothe our unease. For in truth, no one possesses any definitive understanding of what this elusive substance actually is. If it truly constitutes a novel form of matter, then it must be ubiquitous, pervading the cosmos in colossal quantities, literally 5 to 6 times more abundant than all the ordinary, luminous matter we can observe. However, despite countless meticulous attempts spanning decades, employing a vast array of sophisticated detectors and experimental methodologies, every single effort to directly detect this phantom dark matter has, to this day, yielded absolutely nothing. It remains stubbornly invisible, utterly undetectable. Within the framework of the simulation hypothesis, this profound enigma finds a remarkably elegant and elementary explanation. It could simply be a consequence of the limited computational resources of the computer running our simulation. Consider a straightforward analogy from the world of gaming. In the game Spore, for instance, planetary bodies, despite being significantly smaller than Earth, nonetheless simulate Earth-like gravity. This is achieved even though their simulated mass would, in a truly realistic physical model, be entirely insufficient to generate such gravitational forces. Similarly, in our own universe, the architects of the simulation might have simplified the underlying model of our cosmos. They could have drastically reduced the actual quantity of existing objects and particles, optimizing resources, yet simultaneously retained the gravitational effects that these objects should theoretically produce, thereby maintaining the illusion of strong gravity without the computational cost of rendering all the missing mass. In such a scenario, it would also cease to be surprising why the cosmos is predominantly empty, punctuated by absurdly vast distances between celestial objects. While sheer emptiness does not inherently demand an explanation, such pervasive grand-scale inefficiency in the distribution of matter does strike one as curious, perhaps even indicative of an underlying design choice driven by resource management. Adding to the peculiar collection of physical anomalies that obliquely point towards the notion of a simulation is the so-called problem of scale. This issue arises from the observation that, depending on the specific scale of investigation, we are compelled to employ entirely different sets of physical laws to describe phenomena. While Ernest Rutherford, with a characteristic flourish, famously declared that, quote, all science is either physics or stamp collecting, implying a hierarchical unity with physics at its apex, the reality is far more fragmented. No scientist can, with absolute certainty, declare that even the laws of chemistry are entirely derivable from the fundamental laws of physics, let alone the far more complex and emergent laws governing biology, psychology, or sociology. Consider the insightful words of theoretical physicist Sabine Hossenfelder in her book, Existential Physics. Currently, no one can derive the properties of a cell from the properties of its atoms. Indeed, even predicting the properties of molecules is notoriously difficult, a challenge vividly illustrated by the protein folding problem. The mathematics involved are simply too complex. If we are unable to seamlessly integrate the different scales of our reality, if the universe appears to be a patchwork quilt stitched together from disparate, dissimilar pieces, then this certainly provides grounds for, at the very least, profound contemplation. To draw another analogy from our simulated world, in the video game The Sims 2, when transitioning from the highly detailed scale of a single simulated home to the broader, more abstracted scale of an entire city, the game engine necessarily employs different sets of rules and algorithms. Were the intelligent characters within the game to become self-aware and attempt to unify these disparate because these are not inherently unified laws of nature, but rather distinct levels of abstraction, modeled by different computational routines. As Brian Greene warns, simulators must resolve inconsistencies that arise from employing different methods, and they must ensure that the splicing occurs smoothly. This splicing, however, might not always be perfectly efficient. The resulting inconsistencies could accumulate over time, potentially escalating to threatening proportions, leading to a world that proves inconsistent, and thus the simulation would collapse. Even within the established framework of known physics, we currently struggle to unify the laws that govern the very small, quantum mechanics, with those that govern the very large, general relativity. These two pillars of modern physics are not merely incompatible, they fundamentally contradict each other in crucial aspects. And you are already familiar with a dramatic example of this contradiction. In our attempts to merge quantum mechanics and general relativity, we unexpectedly find that an astronaut falling into a black hole is simultaneously both alive and dead, an unresolvable paradox that highlights the chasm between our two greatest theories. Moving beyond these structural inconsistencies, we turn our attention to the intriguing work of James Gates, a theoretical physicist at the University of Maryland. Gates made a startling discovery. Embedded within the mathematical equations that describe the most fundamental underpinnings of our universe, he found intricate structures that bear a striking resemblance to computer error-correcting codes. These sophisticated codes are designed to detect and rectify errors that inevitably arise during the transmission and storage of data, ensuring the integrity of information. Error-correcting codes are ubiquitous in our digital age. They are what allow your internet browser to function reliably, for instance. But the profound question is, why would such mechanisms be present in the fundamental equations I was investigating? Equations pertaining to quarks and leptons, and the theory of supersymmetry, the deepest elements of physical reality. The only other place in nature where a similar, highly complex error correction mechanism is found is within living organisms, specifically in the intricate structure of DNA, where such systems diligently prevent and repair mutations, safeguarding genetic information. But we do not stop here. We now advance to what may be the most profound and unsettling implication of all. David Chalmers, a distinguished cognitive scientist, one of the most popular and influential philosophers of our contemporary era, and notably, the individual commissioned to write an essay for the official Matrix website upon the film's release, openly entertains the possibility that, if we are indeed living within a simulation, then human consciousness itself could be the paramount artifact, the most telling clue, irrevocably pointing to our existence within a computer model. I have frequently encountered a recurring sentiment among both scientists and philosophers. The more deeply we penetrate the laws of the physical world, the more comprehensively we map its intricate mechanics, the further we seem to recede from a genuine understanding of the nature of consciousness. It remains, stubbornly, an enigma wrapped in a mystery, defying reduction to purely physical terms. Consider the insightful words of Max Tegmark in his recent book, Life 3.0. Talking about consciousness is not easy. If you mention the C word in a conversation with an artificial intelligence specialist, a neuroscientist, or a psychologist, they will roll their eyes heavenward. If your interlocutor is your mentor, he might take pity on you and try to dissuade you from wasting your time on a hopeless and unscientific problem. Indeed, my friend Christoph Koch, a renowned neurobiologist and the head of the Allen Institute for Brain Science, once recounted to me how he was explicitly cautioned against pursuing the problems of consciousness until he had secured a permanent professorial position. And this counsel came from none other than Nobel laureate Francis Crick, one of the co-discoverers of the structure of DNA. If you consult the entry for consciousness in the 1989 edition of the Macmillan Dictionary of Psychology, you will find this rather stark assessment, a testament to the field's struggle. Nothing worth reading has been written on this topic. This persistent intellectual void raises a radical possibility. Consciousness may simply not be derivable from the known laws of physics. Let's imagine another thought experiment, a return to the realm of high-fidelity simulations. Suppose a large group of individuals were to have their memories entirely erased, then fitted with advanced virtual reality helmets, and subsequently immersed into the meticulously rendered world of Grand Theft Auto V. What insights might these individuals glean about their new, seemingly real universe? Well, for one, they would quickly ascertain that their universe operates under a set of strict, unwavering laws that dictate the progression of missions, the physics of vehicle operation, the behavior of non-player characters, and the intricate dynamics of the environment. However, here lies the profound crux of the problem. These individuals, deeply embedded within the game, could meticulously dissect the laws of their gaming universe down to its most fundamental algorithmic base, gaining access to the very source code of the game and scrutinizing every last symbol. Yet, within that code, they would find not a single line, not a single instruction, dictating that they must undertake these missions, that they are asterisk obligated to perform any particular action. Their perceived free will would emerge as an inexplicable artifact, a phenomenon utterly irreducible to and non-deducible from the fundamental laws of the GTA 5 universe. The same profound problem, the same inexplicable gap, may apply to our own consciousness. What, precisely, is the nature of that internal voice we perceive within our own minds? This continuous stream of inner speech, this private dialogue we engage in with our conscious selves, does it arise purely and entirely from physical processes, from the electrochemical impulses traversing our neural networks? Or does consciousness emerge from a layer of reality that fundamentally transcends the purely physical world, a property that is emergent and irreducible to its constituent parts? Brian Greene. The truth is, no one, with any degree of certainty, knows whether we will ever be able to successfully simulate consciousness on a computer, precisely because no one truly comprehends what consciousness is. Again, Brian Greene offers a spectrum of possibilities that highlight this profound uncertainty. Perhaps, for any given bundle of connections to become self-aware, it necessitates the presence of a substrate made of convoluted, wet biological material. Perhaps, if intelligent thought is to imbue the inanimate with animation, it requires actual physical molecules, the very constituents of a brain, and not merely the abstract processes and connections between those molecules. It is possible that the informational processes occurring within computers will always differ in some crucial, fundamental way from the activity of a biological brain, thereby precluding the ability to endow computers with genuine sensations and subjective experience. Or perhaps intelligent thought is fundamentally non-physical, as various religious and spiritual traditions contend, and therefore will always remain beyond the reach of technological innovation, regardless of its sophistication. If, indeed, it proves to be fundamentally impossible to simulate consciousness on a computer, then this singular realization would immediately refute an entire class of simulation hypotheses. Specifically, it would directly invalidate Nick Bostrom's probabilistic argument, which hinges on the premise that future advanced civilizations will be able to create conscious simulations. However, even if this particular avenue is closed, a multitude of other fascinating and potentially unsettling scenarios would still remain. For instance, we might be plugged in, much like the individuals in the Matrix, where our physical bodies reside in a real external world, while our consciousness is immersed within a simulated reality. In such a case, a sinister prospect emerges. Not all individuals within the simulated world might be, so to speak, player characters. It is entirely conceivable that some, or even many, of the people who populate your immediate environment are merely empty programs, sophisticated non-player characters, NPCs, devoid of genuine consciousness or subjective experience. The philosopher David Chalmers has popularized the concept of the, quote, philosophical zombie. A philosophical zombie is a hypothetical entity that is, down to its very last atom, physically identical to a human being. It behaves precisely like a human, exhibiting all the outward signs of thought, emotion, and sensation, yet it possesses no actual consciousness. You could poke it with a needle, and it would display a normal human reaction, recoiling, expressing pain. But internally, no one would feel that pain. There would be no subjective experience of suffering. From this chilling perspective, characters like Agent Smith and the woman in red in The Matrix could be considered philosophical zombies. So, perhaps, you might pay closer attention to those individuals around you who seem particularly reluctant to engage in conversations about the nature of consciousness. Yet, if, on the contrary, consciousness is ultimately realizable within a computational framework, if the subjective experience can indeed be simulated on a computer, then this would unleash philosophical consequences of such monstrous proportions that they would dwarf even the most unsettling thought experiments of Boltzmann brains. And I fully comprehend why this particular implication is almost never openly discussed. I will briefly offer one chilling example, leaving the rest for each individual listener to contemplate and extrapolate in the solitude of their own thoughts. You are aware that if the cosmos is truly infinite, then within its boundless expanse, literally everything that is not explicitly forbidden by the laws of physics is not only possible, but indeed happens an infinite number of times. Events that appear to be astronomically improbable, virtually impossible in a finite system, are, in an infinite space, destined to occur an infinite number of times. So then, somewhere within this boundless cosmos, there exists an infinite multitude of stars, classified as red dwarfs. The lifespan of these stars can stretch for tens of trillions of years, an unimaginable duration. Now, if the laws of physics permit the realization of consciousness on a computer, then among this infinite number of red dwarfs, there is an infinite number of red dwarfs that, through sheer cosmic chance, have accumulated around them via solar panels, capsules containing incredibly powerful computers. And on these computers, simulations are running. For instance, a simulation of the video game Cyberpunk 2077, but populated with fully self-aware, sentient beings, experiencing every nuance of joy, despair, pain, and hope. Or, if you are less inclined towards video game analogies, perhaps these computers are running a simulation of, say, a biblical hell, complete with an infinite number of conscious inhabitants doomed to eternal torment. And considering that red dwarfs can radiate energy for trillions of years, and that a computer, as Brian Greene posits, could potentially compute millions of years of human thought in mere seconds, then for the self-aware beings trapped within these capsules, their suffering, or conversely, their bliss, would stretch across an effective eternity, on scales utterly incomputable by human reason. This entire scenario, I concede, sounds like the ravings of madness, a complete flight into schizophrenia. Yet it represents nothing more than the direct, logical consequences derived from the twin premises of an infinite cosmos and the realizability of consciousness within a computational system. An optimist asserts that we live in the best of all possible worlds, and a pessimist fears that this is true. This famous aphorism by James Branch Cabell takes on an entirely new, deeply unsettling and darkly ironic hue when viewed through the lens of these profound cosmic and computational implications. Here, I am compelled to pause. One could, indeed, continue indefinitely, cataloging a seemingly endless array of peculiar artifacts, inconsistencies, and numerical coincidences within our physical reality that, albeit indirectly, lend credence to the notion of our existence within a simulation. However, for the purposes of this particular exploration, such exhaustive enumeration is no longer necessary. My primary objective has been to illustrate that if, as an intriguing possibility, we are truly residing within a virtual reality, then we possess, within our intellectual grasp, the potential capacity to unravel this truth, to delve into its fundamental nature. Our brain, much like any advanced computational system, ceaselessly constructs intricate models of the world, based solely on the raw sensory information it receives through our various sense organs. These internal models are not, crucially, the world itself. They are merely our brain's interpretation, its internal representation, a constantly updated simulation of external reality. And, profoundly, these models often present us with a distorted, even incorrect understanding of the fundamental laws of physics. This is because our bodies and brains, honed over millions of years of evolutionary pressure, were not primarily designed for the precise perception of the universe's ultimate laws. Instead, they were shaped for immediate survival, for navigating a specific environment effectively. We are, for instance, inherently susceptible to optical illusions, our visual system making pragmatic but not always accurate interpretations. We naturally perceive the Earth as flat and stationary, its immense spherical curvature and orbital motion defying our immediate senses. We do not intuitively perceive the subtle yet profound curvature of spacetime induced by massive objects, a cornerstone of general relativity, and so on and so forth. Yet, this relentless, unending quest for answers, this innate human curiosity, has, on at least one pivotal occasion, already guided us to the stunning realization that the reality we experience within the confines of our own minds is, in its essence, a virtual construct. And, strikingly, beyond the boundaries of this internal subjective virtual reality lies a world that is fundamentally, profoundly different from what our raw senses initially suggest. Throughout the long, winding corridor of human history, our intellectual horizons have continuously expanded. First, beyond the immediate confines of our terrestrial home, then, to encompass the vast expanse of our solar system, subsequently, to embrace the unimaginable scale of our galaxy, and, ultimately, to perceive the larger structures of galactic clusters, and so on, in an ever-widening spiral of comprehension. At any given moment, we might experience a sudden, profound awakening, a startling moment of clarity, in which we recognize that the carefully laid trail of intellectual breadcrumbs we have been diligently following inexorably leads us to a truth that lies somewhere beyond the known boundaries of our universe, hinting at even deeper, more fundamental layers of reality. And this potential discovery, whatever its ultimate nature might prove to be, stands as the most magnificent and breathtaking journey in the entire annals of human consciousness. As you drift into the tranquil depths of slumber, allow these concepts to gently weave through your thoughts, not as sources of anxiety, but as quiet invitations to ponder the boundless wonders and elegant mysteries of existence, guiding you smoothly into a restorative and intellectually comforting sleep. This raises a pressing question. If we are indeed embedded within a simulation, will the dedicated scientists, covertly funded by Silicon Valley billionaires, who are desperately seeking a method to extract us, ultimately succeed in their audacious quest? Is such an escape even conceptually possible? Consider a truly iconic moment from the video game Metal Gear Solid, created by Hideo Kojima, a figure so frequently lauded as a genius that the epithet has almost become a meme. In this 1998 classic, there was a cult-status encounter with a boss character named Psycho Mantis. Within the gaming industry, Psycho Mantis is often listed among the greatest antagonists of all time, and for a remarkably innovative reason. During your confrontation with him, the villain abruptly ceases to address the in-game character you are controlling. Instead, he turns his attention directly to you, the player, breaking the fourth wall in a way that was utterly revolutionary for its time. Bear in mind, this was a relatively old game from 1998, and players at that juncture were far less jaded by such meta-narrative tricks. So, when Psycho Mantis began to reveal intimate details about you, the human holding the controller, drawing inferences from your gameplay style, then proceeding to read the memory card within your console and audibly declare the titles of other games you had been playing, and subsequently, with a chilling display of apparent telekinesis, instructed you to place your controller on the floor and, using its built-in vibration function, caused it to visibly move across the room. All of this sent shockwaves through the game. During the ensuing battle, he eerily anticipated your every move, for he literally knew which buttons you were pressing. The only way to defeat him was through a metagame deception, a trick not within the simulated world but in actual reality. Physically unplugging your controller and reinserting it into a different port on the console. Psycho Mantis, it seemed, was acutely aware of his existence within a virtual reality and possessed the astonishing ability to interact with the world beyond the game itself. I believe this serves as an excellent illustration, a compelling thought-provoker, suggesting that, in principle, simulated characters could potentially establish a form of interaction with the external universe that encompasses their simulation. And if we too are inhabitants of a simulation, then the question of whether we can ever escape depends entirely on the nature of that external world. Are our real bodies waiting there in an immense facility, much like the human batteries depicted in The Matrix? Or is our consciousness being itself a simulated construct, all that truly exists, with external experimenters merely conducting some grand sociological study upon us? Perhaps, instead, there exist beings utterly unlike us, beyond our comprehension, who are simply running a high-fidelity simulation of universal evolution, and we are but an incidental byproduct, an emergent complexity within their grand computational experiment. Or, in a more chilling possibility, what if there's nothing but raw, indifferent cosmic space out there? For, as I've mentioned, in an infinite cosmos, the spontaneous, accidental emergence of a simulation-running computer is by definition an ordinary occurrence. What if there is merely an unknowable void, something beyond the very limits of our cognitive capacity to grasp? In short, the external reality could literally be anything imaginable, and indeed many things unimaginable. And there are those who believe that this very mystery is one we should not attempt to solve. In 2019, the philosopher Preston Green published a thought-provoking article wherein he publicly advocated against even attempting to ascertain whether we reside within a simulation. To my knowledge, Green wrote, no physicist proposing simulation experiments has considered the potential dangers of this work. In essence, his argument boils down to a stark risk-benefit analysis. If scientists were to conclusively determine that we inhabit an ordinary, unsimulated universe, we would gain nothing fundamentally new or transformative from this knowledge. However, if they were to discover that reality is, in fact, virtual, the consequences could be catastrophic. For instance, if our simulation is merely a component of some grand sociological or historical research project, then for the scientist residing in the external universe, the entire simulated model holds value only as long as it accurately reflects their own true reality or provides reliable data. Should the inhabitants within the simulation become aware of their simulated status, this newfound knowledge could fundamentally corrupt the integrity of the experiment. Such a model would become tainted, its data rendered useless, and consequently, it would simply be deactivated, the plug pulled, the program terminated. This area of scientific inquiry is fraught with assumptions and uncertainties. But one thing can be stated with certainty. If scientists continue these simulation experiments, the outcomes will either be profoundly uninteresting or extraordinarily dangerous. Is such a risk truly worth taking? Preston Green. Thus, the decision to metaphorically take the red pill, to delve into the very nature of our reality, much like watching this very video, could, in a profound and unsettling sense, be exceedingly perilous. I am entirely serious. You should not, perhaps, delve too deeply into this topic. Ah, but I jest. Let them pull the plug for heaven's sake. We could, after all, unwittingly trigger our own deactivation for reasons entirely invisible to us, simply by continuing to explore the universe, or perhaps, most ominously, by successfully inventing a truly advanced artificial intelligence. Nick Bostrom himself, the very architect of the simulation argument, has extensively explored the potential ramifications of creating a genuinely advanced, superintelligent artificial intelligence. He posits what might transpire should such an entity come into being. A superintelligent agent might assign a high probability to the hypothesis that it exists within a computer simulation model, and that its perceptual sequence is being generated by another superintelligence, which could lead to various convergent instrumental reasons depending on the agent's representation of what type of simulation model it is most likely to be in. Nick Bostrom. In simpler terms, we possess no knowledge of what a superintelligent AI might choose to do if it were to deduce, based on various internal and external cues, that our universe is merely a simulated construct. Perhaps, like the aforementioned psychomantis, it would attempt to interact with the external world in some unforeseen manner, and then the chilling shivers would run down the spines of our own creators, who might then promptly and decisively deactivate our simulation to prevent any further unpredictable interactions or corruptions. As I have consistently emphasized throughout this extended discourse, the simulation hypothesis, in its current formulation, remains an entirely speculative philosophical concept, utterly devoid of any direct, irrefutable empirical proof. Consequently, you are entirely at liberty, by your own volition, to either embrace it as a compelling possibility or dismiss it as an intriguing, yet unsubstantiated, intellectual exercise. However, I personally find great resonance in a particular quotation from Dave Bacon, a specialist in quantum computation, who, in his article What is Computation?, wisely observed, "For the most part, this is just another step in the direction of asserting that the universe is a kind of computer." This point of view has been championed by many researchers, notably Ed Fredkin, Stephen Wolfram, and Seth Lloyd. In many respects, this point of view may be nothing more than the result of the fact that the concepts of computation are the disease of our century. Wherever we look today, we see examples of computers, computations, and information theory, and thus we extrapolate this to our laws of physics. I find this a perfectly balanced and insightful summation, requiring neither addition nor subtraction. Our brain, a tireless information processor, perpetually constructs internal models of the world. These models, sophisticated as they are not the world itself, but rather our personalized, subjective interpretations, filters, and projections. Crucially, these models, shaped by millennia of evolutionary imperatives, are optimized not for absolute, pristine accuracy in deciphering the fundamental laws of the universe, but for the pragmatic purpose of survival within our specific environment. We are, therefore, inherently susceptible to an array of cognitive biases and optical illusions. Our raw senses present us with a flat, seemingly motionless Earth, belying its true spherical form and dynamic celestial motion. We remain oblivious to the subtle, yet profound, curvature of space-time induced by the gravitational influence of massive celestial bodies. And yet, this insatiable, relentless human quest for answers, this inherent, unyielding curiosity, has, on at least one pivotal occasion, already guided us to the stunning realization that the reality we experience within the confines of our own minds is, in its essence, a virtual construct. And, strikingly, beyond the boundaries of this internal, subjective virtual reality lies a world that is fundamentally, profoundly different from what our raw senses initially suggest. Throughout the long, winding corridor of human history, our intellectual horizons have continuously expanded. First, beyond the immediate confines of our terrestrial home, then to encompass the vast expanse of our solar system, subsequently to embrace the unimaginable scale of our galaxy, and, ultimately, to perceive the larger structures of galactic clusters, and so on, in an ever-widening spiral of comprehension. At any given moment, we might experience a sudden, profound awakening, a startling moment of clarity in which we recognize that the carefully laid trail of intellectual breadcrumbs we have been diligently following inexorably leads us to a truth that lies somewhere beyond the known boundaries of our universe, hinting at even deeper, more fundamental layers of reality. And this potential discovery, whatever its ultimate nature might prove to be, stands as the most magnificent and breathtaking journey in the entire annals of human consciousness. As you drift into the tranquil depths of slumber, allow these concepts to gently weave through your thoughts, not as sources of anxiety, but as quiet invitations to ponder the boundless wonders and elegant mysteries of existence, guiding you smoothly into a restorative and intellectually comforting sleep.